Picture a cosmos without a single point of light, no constellations, no galaxies, not even the faintest glimmer against an endless, profound blackness. This was our universe for millions of years after the Big Bang, an expanse so vast and empty that darkness wasn't just an absence, it was the very essence of reality. Yet within that stillness, something extraordinary was stirring. The birth of the first stars didn't just illuminate the cosmos, it transformed it, igniting the chain of events that led to planets, life, and us. Every atom in your body, every element that makes up our world, was forged in the hearts of those ancient, colossal suns. Their story isn't just astronomy, it's our origin story. In this video, we're going to unravel one of the greatest mysteries of the cosmos. How did the first stars form? We'll explore not one or two, but 35 astounding explanations behind their spectacular birth. From the ghostly influence of dark matter to the faint whispers of quantum fluctuations stretched across the universe, each piece of this cosmic puzzle reveals how emptiness gave way to structure, silence to light, and chaos to breathtaking order. You'll discover how gravity sculpted the first pockets of gas, how molecular hydrogen cooled clouds into collapse, and how the universe itself conspired to create the conditions for starlight to dawn. This isn't just a tale of physics and ancient history, it's a journey to the very frontier of human knowledge, where the largest questions about existence find their answers in the smallest details of reality. So join us as we travel back over 13 billion years to witness the moment it all began. Whether you're passionate about space or simply curious about how something came from nothing, you're about to see the universe in a whole new light. Let's begin. For nearly 400,000 years after the Big Bang, the universe was a hot, dense, expanding fog of plasma, a searing, opaque sea of particles and light where nothing could hold together. But then a profound shift occurred. As the cosmos continued to expand and cool, electrons and protons finally combined to form the very first atoms, primarily hydrogen and helium. This event, known as recombination, cleared the cosmic fog. For the first time, light could travel freely across space. This is the light we now detect as the cosmic microwave background, the afterglow of creation itself. But with that light now free to travel, the universe was plunged into darkness. No stars, no galaxies, not a single source of illumination. This epoch is what astronomers call the Cosmic Dark Ages, a period of profound quiet that lasted for millions of years. It was within this deep, pervasive blackness that the stage was silently being set for the most dramatic transformation in cosmic history. This wasn't an empty darkness, though. It was a darkness filled with potential. The universe was now filled with a vast, mostly uniform sea of neutral gas, but it wasn't perfectly smooth. Thanks to tiny quantum fluctuations from the universe's explosive birth, ripples stretched to enormous sizes during a period of hyper-expansion called inflation. There were minuscule variations in density. Some regions were ever so slightly denser than others, and in a universe now dominated by matter and not radiation, gravity could finally get to work. Those slightly denser patches had slightly stronger gravitational pulls. Over millions of years, this relentless force began to slowly, painstakingly, drag surrounding gas toward them. They were the seeds from which everything, stars, galaxies, clusters, would eventually grow. Understanding this process is one of the great triumphs of modern cosmology. Scientists can't build a time machine to go back and watch it happen, but they can build incredible digital universes inside supercomputers. These sophisticated simulations start with the conditions we see imprinted in the cosmic microwave background, and then run the laws of physics forward in time. They show us how those tiny density fluctuations, under the relentless influence of gravity, slowly evolve. The slightly denser regions become more pronounced, drawing in more matter, growing heavier and more massive. Over immense timescales, they begin to form the first large-scale structures, vast filamentary webs of dark matter with gas flowing along them, pooling at the intersections into what we call protogalactic clouds. These dark matter halos provided the essential gravitational scaffolding, the hidden architecture upon which the visible universe would be built. This entire period was a necessary prelude. The universe had to expand and cool enough for atoms to form. It had to become transparent so that matter could collapse without being pushed apart by radiation pressure. And it needed those initial imperfections, those cosmic seeds, to give gravity a starting point. Without any one of these conditions, the cosmos might have remained a forever dark, forever smooth, and forever barren expanse. Instead, this foundational era created an environment that was, for the first time, ripe with potential. It was a universe poised on the brink of ignition, waiting for the next physical processes to kick in and turn these gathering clouds of gas into the first brilliant beacons of light. Yet within that profound darkness, something crucial was brewing, the raw material for creation itself. The early universe was a remarkably simple place, chemically speaking. After the initial fury of the Big Bang settled, the cosmic palette contained only the three lightest elements: hydrogen, helium, and a tiny, almost negligible sprinkling of lithium. There was no carbon, no oxygen, no iron, none of the complex elements that make up our world and our bodies today. This pristine, primordial gas became the exclusive fuel for the very first stars. Think of it as a universe working with a minimalistic toolkit, but one that was perfectly designed for the task at hand. This fundamental simplicity wasn't a limitation. It was the key that unlocked the door to starlight. This pure composition led to stars that were utterly different from the ones we see today. Our Sun, for example, is a metal-rich star, meaning it contains a significant amount of elements heavier than helium, all forged in the hearts of previous generations of stars that lived and died long before our solar system was even a glimmer. Those heavier elements, which astronomers call metals, play a huge role in how modern stars form. They are incredibly efficient at absorbing radiation and cooling down giant clouds of gas. This might sound helpful, but it actually causes the cloud to fragment into many smaller, denser clumps. That's why star formation in today's universe often results in whole clusters of stars, most of which are relatively small, like our Sun, or even smaller. But the first stars had no such ingredients. Their fuel was pure hydrogen and helium. This lack of metals had a dramatic effect on the entire process of star birth. Without those heavy elements to help cool the gas, the primary cooling mechanism had to come from molecular hydrogen. Now, molecular hydrogen is good, but it's not nearly as efficient as metal-based cooling. This might sound like it would be a problem, but it had a surprising consequence. Because the gas couldn't cool down as effectively, it stayed hotter during the gravitational collapse. And in the physics of star formation, hotter gas has higher pressure, which resists collapse. This might seem counterintuitive, but it actually meant that only the very largest, most massive clouds of gas could overcome this thermal pressure and collapse all the way down to form a star. The result, the first stars weren't just a little bigger, they were behemoths, true cosmic titans. Scientists estimate that these first stars, often called population 3 stars, could have been hundreds of times more massive than our Sun. Imagine a star so colossal that it would dwarf our entire solar system. Their immense size directly dictated their destiny. Larger stars burn their nuclear fuel with ferocious speed and intensity. They live fast and die young, shining with a brilliance that is almost incomprehensible, millions of times brighter than our sun. But their lifetimes were tragically short, perhaps only a few million years before they exploded in spectacular supernova. These cataclysmic deaths were not an end, but a beginning. It was in these violent explosions that the universe finally forged the first heavy elements, seeding the cosmos with the metals that would eventually form rocky planets, oceans, and life itself. So the very simplicity of the primordial gas set in motion the chain of events that would, billions of years later, make our existence possible. But while the simple chemistry of hydrogen and helium set the rules for how the first stars would form, there was another, far more mysterious force at work behind the scenes, shaping the entire process. We now turn to the invisible architect of cosmic structure, dark matter. This enigmatic substance, which neither emits nor absorbs light, has never been directly observed, yet its gravitational influence is written across the cosmos. In the early universe, dark matter was the essential scaffolding upon which the first stars were built. Think of it like this: if the primordial gas was the lumber and bricks for construction, dark matter was the hidden framework, the blueprint and support beams that gave the entire project its shape and stability. Without it, the universe might have remained a formless, starless expanse forever. So how does something we can't see wield such immense power? The answer lies in gravity. Dark matter makes up about 85% of all the matter in the universe, meaning it vastly outweighs all the atoms, planets, and stars we can see. After the cosmic microwave background was emitted, this dark matter began to clump together first, responding to those tiny density fluctuations from the Big Bang. Because it doesn't interact with light or other electromagnetic forces, it doesn't feel radiation pressure. This allowed it to start collapsing into structures long before the regular atomic gas could. These clumps of dark matter formed what scientists call halos, vast, spherical clouds of invisible mass with an incredibly powerful gravitational pull. These dark matter halos became the gravitational engines of star formation. As they grew, they created deep potential wells. Think of them as cosmic potholes or valleys in the fabric of spacetime. The ordinary atomic gas, composed of hydrogen and helium, then flowed into these gravitational valleys. The dark matter provided the immense pull necessary to gather the gas from the surrounding, more diffuse regions of the universe, concentrating it into clouds dense enough for gravity to finally trigger collapse. It's a cosmic partnership. The dark matter provides the overwhelming gravitational muscle, and the baryonic gas provides the raw material that eventually ignites into starlight. Without these dark matter anchors, the slight tug of the gas's own gravity would have been far too weak to pull anything together before the expansion of the universe diluted everything into nothingness. This partnership explains why the first stars didn't just form anywhere. They formed at the hearts of these specific dark matter concentrations. The smallest, earliest halos, known as minihalos with masses perhaps 1,000,000 times that of our Sun, acted as the nurseries for the very first stellar giants. The distribution of dark matter dictated the distribution of the first light. This invisible framework didn't just help things along, it was absolutely essential. It amplified the faint whispers of density from the Big Bang into shouts that could be heard across the cosmos, gathering matter at a rate that ordinary gravity alone could never have achieved. Dark matter was the universe's silent, unseen partner, patiently and relentlessly constructing the stage upon which the drama of the first dawn could finally begin. But how could something as vast and majestic as a star begin from what was essentially a perfectly smooth, expanding universe? The answer lies in the realm of the incredibly small, in the ghostly, probabilistic world of quantum mechanics. It's almost poetic that the largest structures we see in the cosmos owe their existence to the tiniest, most fleeting events imaginable. In the very first fraction of a second after the Big Bang, the universe was a seething, energetic foam where the laws of physics as we know them break down. At these unimaginable scales of energy and size, empty space itself is not truly empty. It is a turbulent sea of potential, where pairs of particles and antiparticles constantly flicker in and out of existence, borrowing energy from the vacuum for the briefest of moments before annihilating and returning it. These are quantum fluctuations, tiny, random wrinkles in the fabric of spacetime itself. Under normal circumstances, these fluctuations are utterly insignificant and vanish without a trace. But the early universe was anything but normal. It underwent a period of hyper-expansion called inflation, where it ballooned in size by an astronomical factor in an infinitesimally small amount of time. This rapid stretching had a profound effect on those quantum wrinkles. Imagine taking a tiny, microscopic imperfection on the surface of a balloon and then inflating that balloon to the size of the entire Earth. That tiny imperfection would now be a massive, continent-sized feature. In the exact same way, inflation stretched those minuscule quantum fluctuations from the subatomic scale to sizes encompassing millions of light-years. They were frozen into the very fabric of the expanding cosmos, becoming the first real structures, not structures of matter, but structures of density. Some regions were left ever so slightly denser than others. These were not the clumps of matter that would become stars. They were the seeds of possibility, the faint gravitational blueprints that would eventually guide the formation of everything. Without these initial imperfections, gravity would have had nothing to work with. A perfectly smooth, perfectly uniform universe would have remained just that smooth and uniform. Gravity pulls equally in all directions if matter is evenly distributed. It needs a starting point, a slight lumpiness to amplify. Those quantum fluctuations, magnified by inflation, provided that crucial initial push. They created the gravitational wells, however shallow at first, that would begin to pull in surrounding matter. Over hundreds of millions of years, the slightly denser regions would pull in more gas, growing denser and more massive, while the slightly emptier regions would be drained further. This process of gravitational amplification is what ultimately led to the vast cosmic web of dark matter and the gathering clouds of primordial gas we discussed earlier. This explanation is truly astounding because it connects the grandest scales of the cosmos, the distribution of galaxies and the birth of stars, to the most fundamental laws of particle physics. The first stars did not just appear at random. Their locations, their distribution across the sky, and their very existence can be traced back directly to these random quantum events in the first moment of time. It means that the pattern of the night sky, with its glittering tapestry of stars and galaxies, is ultimately a fossilized record of the universe's quantum mechanical origins. We are seeing the amplified echo of a whisper from the dawn of time, a testament to the idea that from the smallest uncertainty, the greatest structures can emerge. While those quantum fluctuations provided the initial blueprint, they were just the starting point. A blueprint alone doesn't build a house. You need a powerful force to do the construction. In the cosmos, that force is gravity. After inflation, the universe was a vast, expanding sea of matter, but it was a sea with gentle ripples, those tiny density variations we just discussed. For millions of years, not much seemed to happen, but gravity is patient and relentless. In those regions that were ever so slightly denser, the gravitational pull was a tiny bit stronger. This minute difference allowed them to start acting like cosmic magnets, ever so slowly drawing in the sparse atoms of hydrogen and helium from their surroundings. It was an incredibly gradual process, but over astronomical timescales, it became a runaway effect. As a region gained mass, its gravitational pull increased, allowing it to attract even more matter, which further increased its pull. This positive feedback loop is the heart of gravitational instability. This gathering of matter wasn't a gentle snowfall, it was a violent, accelerating collapse. As enormous clouds of primordial gas were pulled inward, they began to condense. And in physics, when you compress a gas, it heats up. Think of a bicycle pump. As you compress the air inside, the pump barrel gets warm. The same principle operated on a cosmic scale, but the temperatures and pressures involved were almost beyond comprehension. At the center of these collapsing clouds, the density and temperature began to soar. Yet, for a star to be born, this cloud couldn't just collapse into a single point and rebound. It had to find a way to shed energy, to cool down just enough to allow the dense core to form without being supported by the immense thermal pressure generated by the collapse. This is where the unique chemistry of the early universe came into play, allowing the gas to cool through the radiation of molecular hydrogen, a process we'll explore in more detail soon. The entire mechanism hinges on a critical balance between two opposing forces: gravity, which wants to pull everything inward, and pressure, which pushes outward, resisting that collapse. For eons, the expansion of the universe kept these forces in check, but eventually, in the densest regions, gravity won the tug of war. The moment a cloud of gas crosses this threshold and begins to collapse under its own weight is a foundational moment in astrophysics. It's the point where a quiet patch of the universe transitions from being a passive structure to an active stellar nursery. This process of gravitational collapse doesn't just create stars. It is the universal engine that has built every luminous object we see in the night sky, starting with the very first ones. What's truly fascinating is how this process was both universal and unique for the first stars. The same basic physics of gravitational instability governs star formation in our galaxy today. However, the environment was entirely different back then. Modern star-forming clouds are filled with dust and complex molecules that are incredibly efficient at cooling the gas, allowing it to fragment into many smaller clumps that become low-mass stars like our Sun. But in the pristine early universe, without those efficient coolants, the process was much more straightforward and, in a way, more brutal. The clouds couldn't fragment as easily. They collapsed more monolithically, often forming a single, tremendously massive object at the center, rather than a whole cluster of smaller stars. This direct, efficient collapse, fueled purely by gravity and basic molecular cooling, is why astronomers believe the first stars were likely giants, hundreds of times more massive than our Sun, burning ferociously bright and dying spectacularly young. Gravitational instability is more than just a theory. It's a narrative of transformation. It describes how the faintest whisper of extra density can, through the unwavering application of a fundamental force, snowball into a cosmic revolution. It is the story of how a formless, dark universe used its own inherent properties to gather itself together and ignite, ending the cosmic dark ages and flooding the void with light for the very first time. This relentless pull of gravity didn't just make stars, it set the entire cosmic cycle in motion, forging the first heavy elements that would eventually seed the universe with the ingredients for planets and life. But for all its immense power, gravity couldn't have done the job alone. It had a crucial partner in this cosmic dance, one that worked on an atomic level to overcome a fundamental obstacle. As those vast clouds of primordial gas collapsed under their own weight, they faced a serious problem: heat. You see, when you compress any gas, its temperature rises dramatically. Think of it like this: a giant cosmic version of that bicycle pump we mentioned earlier. As gravity pulled more and more hydrogen and helium inward, the particles were squeezed closer together, colliding more frequently and transferring energy. This generated immense thermal pressure, an outward force pushing back against the inward crush of gravity. If this pressure couldn't be relieved, the cloud would simply stabilize, reaching a state of equilibrium where it could hover in a sort of limbo, too hot to collapse further but held together by gravity, a failed star known as a brown dwarf. For the first stars to ignite their nuclear furnaces, the gas needed to reach incredibly high densities, and to do that, it had to find a way to cool down. This is where a seemingly simple molecule enters the story as the universe's first and most important air conditioner, molecular hydrogen, or H2. In the modern universe, giant clouds of gas are filled with complex molecules and tiny particles of dust. These are superb at radiating away heat, allowing the cloud to cool rapidly, fragment, and form many smaller stars, but the early universe had none of that. It was pristine, pure hydrogen and helium. Atomic hydrogen, a single proton with a single electron, is not very efficient at cooling. It takes a very specific, rare collision for it to release a photon of light and shed energy. The universe needed a better way, and it found it through a delicate and fascinating bit of chemistry. As the gas swirled in those dark matter halos, occasional collisions occurred between hydrogen atoms. Sometimes two atoms would briefly stick together, forming a fragile, temporary molecule. But more importantly, free electrons could act as catalysts, attracting protons and facilitating the formation of a more stable molecular hydrogen bond. It was a slow process, but over millions of years, trace amounts of this molecule began to accumulate within the collapsing clouds, and molecular hydrogen has a special talent. Its structure allows it to vibrate and rotate in specific ways. When it collides with another atom or molecule, it can absorb some of the kinetic energy from that collision and then release it by emitting a low-energy infrared photon. This photon, this tiny packet of light, could then travel straight out of the gas cloud, carrying the unwanted heat with it into the void of space. This was the critical release valve. By radiating away this thermal energy, the gas cloud could lose its supporting pressure, allowing gravity to continue its relentless work unchallenged. The cloud could contract further, densities could increase, and temperatures could continue to rise at the core, all because this simple molecule was efficiently dumping the heat generated by the collapse. It was a beautiful negative feedback loop. Gravity causes collapse, collapse causes heating. Heating enables more molecular hydrogen formation through collisions, and that molecular hydrogen cools the cloud, allowing for further collapse. The efficiency of this cooling process directly dictated the fate of the first stars, because molecular hydrogen cooling, while effective, is not as powerfully efficient as the metal-based cooling we see today. It had a profound consequence. The gas couldn't cool down to the very low temperatures seen in modern star-forming regions. It stayed relatively warm, which meant the internal pressure remained fairly high. In star formation, there's a concept known as the Jeans mass, the minimum mass a cloud must have to overcome its internal pressure and collapse. Warmer gas with higher pressure has a much larger Jeans mass. This is why the first stars are predicted to have been so incredibly massive. Only the very largest, most massive clouds of gas could muster enough gravitational force to overcome that warmer gas's resistance and complete the collapse. Without molecular hydrogen, even that might not have been possible. The clouds may have stagnated, but with it, the path was clear, albeit a path that led to the creation of colossal, brilliant, and short-lived stellar giants. This humble molecule, formed from the two most basic particles in the universe, was the unsung hero that made the first light possible. Now, If we shift our perspective from the microscopic interactions of gas to the grand architecture of the cosmos, we see an even more intricate process at work. The universe didn't just build stars one by one in isolation. It constructed them within a vast, evolving framework, piece by piece. This brings us to a cornerstone concept in modern cosmology known as hierarchical structure formation. This is the powerful idea that the universe builds itself from the bottom up, starting with the smallest structures and assembling them over immense timescales into the majestic galaxies and clusters we see today. It's a cosmic version of starting with individual bricks, building walls, and then assembling those walls into a cathedral. For the first stars, this process meant they weren't born in grand, ready-made galaxies, but in the universe's smallest, humblest neighborhoods, the minihalos of dark matter. These minihalos were the true cradles of the first light. Imagine them as the earliest, most primitive gravitational traps. They formed first because they required the least amount of mass to collapse under their own gravity. We're talking about structures with masses perhaps only a few 100,000 times that of our Sun, a tiny speck by cosmic standards, within the vast filamentary web of dark matter that was slowly weaving itself together. These mini-halos were the knots at the intersections. Their gravitational pull, though modest, was just enough to begin gathering the primordial hydrogen and helium gas from their surroundings. They provided a protected environment, a gravitational nest where the gas could settle, begin to cool through molecular hydrogen, and finally reach the densities needed to trigger collapse. It was inside these countless, tiny dark matter cocoons that the first protostars began to flicker to life. But the story doesn't end there. The universe is dynamic and constantly in motion. Gravity continued to work on an even larger scale, pulling these minihalos toward one another. They began to merge, to collide, and to accumulate. When two of these halos merged, it wasn't a destructive crash, it was a creative act. Their dark matter combined to form a larger, more massive halo. The gas clouds they each carried were violently stirred together, a process that often triggered massive waves of new star formation. This bottom-up assembly continued relentlessly. Small minihalos merged to form larger dwarf galaxies, and these dwarfs then merged to form the majestic spiral and elliptical galaxies we recognize today. Our own Milky Way galaxy is the product of billions of years of this hierarchical growth, having consumed countless smaller galaxies throughout its long history. This layered model elegantly explains so much of what we observe. It tells us why the very first stars were so isolated and likely so massive. They formed in the smallest, quietest environments where feedback and competition were minimal. It then explains how later generations of stars, formed in the turbulent mergers of these halos, would have had a wider range of masses as gas clouds were shocked and fragmented. Supercomputer simulations are vital here, allowing us to watch this cosmic dance play out over billions of virtual years. These simulations show us how the dark matter skeleton of the universe forms first, with gas flowing along its filaments and pooling at its nodes, and how the lighting up of the universe, the epoch of first light, follows this underlying pattern of growth. The distribution of the first stars wasn't random. It was a direct imprint of this hierarchical construction, a signature of a universe building itself from the ground up, one tiny piece at a time. Yet, even as the first stars began their spectacular lives, they sowed the seeds of their own limitation, giving rise to a powerful self-regulating force known as radiation feedback. In today's universe, this is a dominant process. When massive stars ignite, they flood their surroundings with intense ultraviolet radiation. This high-energy light is like a cosmic blowtorch, heating the surrounding gas clouds, breaking apart molecules, and ionizing atoms, stripping them of their electrons. This heating dramatically increases the internal pressure of the gas, making it puffy and resistant to collapse. It can even blow the gas away entirely, shutting down star formation in that region for millions of years. This feedback process is why we see cycles of star birth and death in galaxies. It's a balancing act between creation and destruction. But for the very first stars, this story played out differently, and that difference was absolutely crucial. These pioneer stars enjoyed a unique and fleeting period of grace. They formed in a universe that was still almost entirely dark and neutral. There was no background sea of ultraviolet radiation yet because, well, they were the first. Each of these colossal stars ignited in profound isolation, separated by vast stretches of empty space from any others. This meant that when a first star turned on, its fierce radiation only affected its immediate surroundings. The rest of the universe remained a pristine, cool, and neutral canvas, untouched by this new light. There was no pre-existing radiation field to interfere with the delicate process of gravitational collapse happening in other, faraway minihalos. Each star-forming region was essentially its own closed experiment, operating without any external influence or disruption from its stellar neighbors. This isolation had a profound consequence. It allowed star formation to proceed with a kind of unbridled efficiency that the universe would never see again. Without the disruptive effects of external radiation, gas clouds could collapse monolithically. There was no external energy source to heat the gas, increase its pressure, or rip apart the fragile molecular hydrogen molecules that were so vital for cooling. Gravity could work its magic unimpeded, pulling in enormous amounts of material onto the growing protostar at the core. The accretion rates, the speed at which gas fell onto the star, were likely staggering, far exceeding anything we observe in modern nebulas. This unimpeded inflow of fuel is a key reason why astrophysicists believe the first stars achieved such breathtaking masses, potentially reaching several hundred times the mass of our Sun. This period of minimal feedback was, by cosmic standards, incredibly brief. The moment the first star began shining, the clock started ticking. Its ultraviolet photons began to create a growing bubble of ionized hydrogen around it, a so-called H-II region where the gas was heated to thousands of degrees and stripped of electrons. For that single star, it began altering its own nursery. But more importantly, when these behemoths reached the end of their short lives, a few million years later, they died in spectacular supernova explosions. These explosions did two things. They blasted newly forged heavy elements out into space, and they flooded the cosmos with even more intense radiation. This ended the era of purity. Once the universe was seeded with metals and permeated by a background glow of ultraviolet light, the rules of the game changed forever. Future generations of stars would form in environments where radiation feedback was a constant and limiting factor, leading to smaller stars and richer clusters. The first stars, therefore, were products of a unique and unrepeatable moment, a golden age of formation where they could blossom in silent, dark isolation, free from the interfering light of their predecessors. While the relentless pull of gravity and the delicate cooling of molecular hydrogen set the stage, the story of the first stars wasn't a simple, orderly collapse. The early universe was far from a placid sea of calm gas. It was a churning, turbulent cauldron. This brings us to a powerful and often overlooked actor in the drama of cosmic dawn, turbulence. Imagine trying to stir a vast, invisible pot of primordial soup. Within these massive clouds of hydrogen and helium, there were chaotic, supersonic motions, swirls, eddies, and shock waves rippling through the gas. This wasn't a gentle stirring. It was a violent, chaotic mess of motion that played a surprisingly constructive role in building the first structures. This turbulence acted like a cosmic whisk, creating a highly non-uniform environment. Within a single, large cloud, some regions would be caught in powerful inward flows, compressing the gas to much higher densities. Other regions would be stretched thin by outward motions. These random compressions created localized pockets where the density was significantly higher than the average. And in the game of gravity, density is everything. A region that is just a little denser has a slightly stronger gravitational pull, giving it a head start in the race to collapse. Turbulence, therefore, provided the initial push, creating the dense seeds that gravity could then amplify. Without these turbulent motions, the gas might have remained too smooth, and the collapse might have been much slower, or perhaps even stalled altogether, waiting for random atomic motions to accidentally create a density enhancement, which could take eons longer. But turbulence did more than just create the initial clumps. It also played a vital role in determining the final product. In the modern universe, turbulent clouds fragment into many small pieces, leading to the birth of entire star clusters. For the first stars, the effect was similar but on a different scale. The chaotic flows helped to break up the massive primordial clouds into smaller, collapsing cores. This fragmentation process is crucial because it likely prevented the formation of a single, impossibly gigantic star in the center of every cloud. Instead, turbulence probably helped create multiple massive stars within one region, or perhaps even a few smaller companions alongside the true behemoths. This means turbulence is a key factor in explaining the predicted mass range of the first stars. It wasn't just a population of lonely monsters, but perhaps small families of brilliant siblings, each born from the same turbulent nursery. The source of this early chaos is a fascinating puzzle itself. Some of it was likely primordial, a leftover echo from the violent birth of the universe during the Big Bang, imprinted as faint ripples in the motion of the gas. Another major source was the gravitational landscape itself. As dark matter halos merged and grew through the hierarchical process we discussed, these collisions would have sent powerful shock waves reverberating through the gas within them, stirring it up violently. It's a dynamic feedback loop. Gravity builds the structures that create the turbulence, and that turbulence then enhances gravity's ability to form stars within those structures. This intricate dance between force and motion added a necessary layer of complexity to the early universe, ensuring that the first stars were not all identical, but instead displayed a diversity in their masses and births, setting the template for all the stellar variety we see in the universe today. While we often picture the early universe as a realm dominated solely by gravity and simple gases, there's another, more subtle force that may have quietly shaped the birth of the first stars: magnetism. We're so accustomed to thinking about magnetic fields in the context of planets, stars, and galaxies today that it's easy to forget they had to come from somewhere. The question of whether primordial magnetic fields existed in the infant cosmos and what role they might have played opens up a fascinating and still unfolding chapter in our story. These fields wouldn't have been anything like the powerful magnets we know now. They would have been incredibly faint, whispers of structure woven into the fabric of space-time itself. Yet, even a whisper can change the course of a flowing river, and these weak magnetic fields could have gently guided the collapse of the very first gas clouds. The origins of these potential fields are a topic of intense speculation among physicists. One compelling idea is that they were generated during the universe's most violent and energetic early moments. During the period of rapid inflation, when space-time itself expanded faster than the speed of light, quantum fluctuations could have been stretched into not just density variations, but also electromagnetic ones. Alternatively, moments later, as the universe cooled and underwent fundamental phase transitions, like water freezing into ice, the dynamics of the primordial plasma could have spontaneously generated magnetic fields through chaotic motions. Whatever their source, if they existed, they would have been imprinted across the entire cosmos, a vast, faint, and mostly invisible web of magnetic force lines waiting for matter to flow along them. So how would something so weak have any effect on the colossal process of star formation? The key lies in the incredible scales of time and space involved. Over millions of years, even an imperceptibly weak magnetic field can influence a slowly collapsing cloud of ionized gas, a plasma where charged particles are present. As this gas begins to move, these charged particles interact with the magnetic field lines, effectively getting caught on them like beads on a wire. This interaction can do two important things. First, it can provide a small amount of additional support against gravity's relentless crush, a kind of magnetic pressure that could slightly slow down the collapse. Second, and perhaps more importantly, it can channel the flow of material. Magnetic fields can act as a guide, directing infalling gas into specific patterns, influencing how a cloud rotates, and determining where it might preferentially fragment into multiple clumps instead of a single monolithic object. This guiding hand would have had a direct impact on the properties of the first stars. For instance, magnetic fields are excellent at transporting angular momentum, the spin of a collapsing cloud. A cloud always has some inherent spin from the turbulent motions of the universe, and as it collapses, this spin accelerates, much like a figure skater pulling in their arms. If this spin isn't dissipated, it can create a barrier that prevents further collapse, leading to a disk instead of a dense star. Primordial magnetic fields could have acted as a brake, transferring that rotational energy outward and allowing the central core to continue contracting. This process might have been crucial for enabling the formation of a single, massive star at the center rather than a fragmented binary system. Furthermore, by influencing the fragmentation process, these faint fields could have played a role in determining the initial mass function of the first stars, perhaps making a wider range of masses possible, from the true behemoths to slightly smaller, though still enormous, objects. It's important to note that this remains one of the more debated explanations in the field. Detecting evidence of these primordial fields is extraordinarily difficult, and their simulated effects are often subtle, sometimes dwarfed by the overwhelming power of gravity and the effects of dark matter. Yet the possibility is too compelling to ignore. It introduces the full force of electromagnetism into the narrative of cosmic dawn, not just as a consequence of the first stars, but as a potential architect. It suggests that the universe's first light may have been kindled under the influence of a silent, invisible guidance system, a magnetic memory from its very first moments that helped write the rules for how the darkness would finally end. We've explored how dark matter's gravity sculpted the cosmic landscape and how magnetic fields might have provided subtle guidance, but there's an even more intimate and elusive possibility to consider. What if dark matter didn't just shape events from the shadows through its gravity, but actually reached out and touched the ordinary matter of the early universe? This brings us to a profoundly nuanced and speculative idea: direct interactions between dark matter particles and the baryonic gas that would become the first stars. For the most part, our standard cosmological model treats dark matter as a ghostly presence. It feels gravity and can clump together, but it doesn't interact with light or ordinary matter in any other significant way. It simply passes through everything, including itself, as if it weren't even there. This is known as the collisionless cold dark matter model, and it has been incredibly successful at explaining the large-scale structure of the universe. But what if that story isn't the complete picture? What if there was a faint, whisper-thin thread of connection? Some theoretical physicists propose that dark matter particles might have experienced very rare, weak interactions with protons, electrons, and nuclei, the baryonic particles that made up the primordial gas. These wouldn't be dramatic collisions. Think of them more like two ships passing in the night, barely brushing against one another in the vast darkness. Even if only 1 in a billion dark matter particles ever interacted with a gas particle, over millions of years within a dense, collapsing cloud, that tiny effect could have accumulated into something meaningful. These interactions would have acted as a conduit, a way for energy and momentum to be transferred between the invisible dark matter and the visible gas. This could have subtly altered the thermal history of the gas cloud, either providing a minuscule amount of extra heating or offering a novel mechanism for cooling. Let's consider the cooling scenario, as it's particularly intriguing. If a dark matter particle were to collide with a gas particle, it could effectively carry away a little bit of the gas's kinetic energy, its heat, and then deposit that energy elsewhere as it traveled through the cloud or even out of it entirely. This would be an entirely new form of cooling, one that operated alongside the molecular hydrogen cooling we discussed earlier. In regions of a dark matter halo that were especially dense with these particles, this extra cooling could have made the gas even more efficient at collapsing, potentially accelerating the birth of the first stars and maybe even allowing smaller, less massive clouds to overcome their internal pressure and form stars where they otherwise couldn't have. Conversely, if the interactions tended to heat the gas, they could have provided a small source of pressure that slightly resisted gravitational collapse, potentially delaying star formation or making it less efficient in certain areas. The impact of these hypothetical interactions wouldn't have been uniform across the entire early universe. It would have been strongest in the very centers of the first dark matter minihalos, where the concentration of both dark matter and gas was at its peak. This means that the first stars to form might have been influenced by this effect more strongly than stars that formed later on in less dense environments. It introduces a fascinating layer of variety and patchiness to the process of cosmic dawn. This isn't just a story about gravity and gas physics anymore. It's a story that potentially ties the formation of the first luminous objects directly to the fundamental properties of the universe's most mysterious substance. It suggests that the nature of dark matter itself, its mass, its interaction cross-section, its very identity could have left an imprint on the timing, location, and even the size of the very first stars. While this remains a highly theoretical frontier, it powerfully illustrates how the quest to understand the first stars is inextricably linked to the deeper quest to uncover what dark matter actually is. Now, let's venture into one of the most intriguing and speculative ideas in all of cosmology, a concept that connects the birth of the first stars to the most voracious objects in the universe. We've talked about dark matter providing the gravitational scaffolding and molecular hydrogen enabling the cooling, but what if there was another, even more powerful player hiding in the primordial darkness? Imagine not just a region of slightly denser gas, but a point of infinite density, a cosmic singularity with a gravitational pull so fierce that not even light could escape it. This is the realm of primordial black holes, and if they existed, they could have radically accelerated the entire timeline of cosmic dawn. The standard model suggests the first stars took hundreds of millions of years to form, but some observations hint that structure in the universe might have gotten started surprisingly early. Primordial black holes offer a tantalizing solution to this puzzle. Unlike the stellar mass black holes formed from collapsing stars or the supermassive ones at galactic centers, primordial black holes wouldn't need a star to die first. Theorists propose they could have been created in the unimaginably dense and turbulent environment of the very early universe, mere instants after the Big Bang. Tiny fluctuations in density could have collapsed directly into black holes with a wide range of masses, some as small as an asteroid, others as massive as 1,000 suns. These ancient objects would then have been scattered throughout the expanding cosmos, long before the first star ever flickered to life. So how does a black hole help make a star? It acts as the ultimate nucleation site, a gravitational anchor of unbelievable power. In a universe that was mostly smooth and homogeneous, these black holes would have been extreme outliers. Their immense gravity would have acted like a cosmic magnet, relentlessly pulling the surrounding hydrogen and helium gas toward them. This process, called accretion, would have created a swirling, superheated disk of material around the black hole, but it also would have dramatically increased the density of gas in its immediate vicinity. Think of it like a snowball effect. The black hole's gravity gathers the gas, and this gathering makes the local region denser, which in turn amplifies the overall gravitational pull of the entire cloud, making it far easier for it to overcome internal pressure and collapse. A primordial black hole sitting at the heart of a dark matter minihalo wouldn't just be a participant in star formation. It would be the catalyst, kicking the process into overdrive and potentially forming stars tens of millions of years earlier than otherwise possible. The influence wouldn't stop there. As gas spiraled inward at a significant fraction of the speed of light, the tremendous friction within the accretion disk would have heated it to millions of degrees, causing it to emit copious amounts of high-energy radiation. This intense light could have provided a unique and powerful feedback mechanism. In some cases, this radiation might have blown away nearby gas, temporarily suppressing star formation. But in other scenarios, particularly with smaller black holes, the energy output might have been just enough to help ionize and stir the gas, perhaps even enhancing the formation of molecular hydrogen and actually promoting the cooling and collapse processes in the outer regions of the cloud. Furthermore, the sheer kinetic energy of the infalling matter could have generated powerful jets and outflows, sculpting the gas cloud and creating dense shells at their edges where the compression might trigger a wave of new star formation around the central black hole itself. This explanation, while highly speculative, is powerful because it connects two great mysteries: the nature of dark matter and the rapid appearance of early structure. Some theories even suggest that certain types of primordial black holes could themselves be a form of dark matter. If that were true, then the dark matter halos we've discussed wouldn't just be made of unknown particles. They would be built around these central, ancient black holes, providing a double gravitational punch that would make gas accumulation incredibly efficient. While the search for definitive evidence of these primordial objects continues, their potential role serves as a thrilling reminder that the story of the first stars is still being written, and the answers may lie with some of the most extreme and enigmatic phenomena the universe has ever conceived. To truly grasp the significance of cosmic inflation, we need to rewind the clock even further back than the Dark Ages, to a time so early that the very concepts of matter and energy were just beginning to take shape. In the first fleeting fraction of a second after the Big Bang, the universe is thought to have undergone a period of hyper-expansion, ballooning from a subatomic speck to something vastly larger in an almost incomprehensibly short burst. This wasn't just any expansion, it was a violent stretching of spacetime itself, and it left an indelible mark on the cosmos, a legacy that would dictate not only the distribution of the first stars, but the very large-scale architecture of the universe we see today. This inflationary period did far more than just make the universe enormous. It took the faintest whispers of the quantum world and magnified them into the foundational blueprints for creation. Remember those quantum fluctuations we discussed, the tiny, temporary ripples in energy that flicker in and out of existence in the vacuum of space. Inflation seized upon these microscopic imperfections and stretched them across the cosmos, freezing them into the fabric of reality as permanent variations in density. But it didn't do this randomly. The physics of inflation imprinted a very specific statistical signature on these fluctuations, a predictable pattern that astronomers call a nearly scale invariant spectrum. In simpler terms, this means that the universe was left with density variations that were almost perfectly uniform in their amplitude, regardless of the size of the region you look at. Whether you examine a patch of space the size of a solar system or a patch the size of a supercluster, the initial lumpiness would have been remarkably similar. This precise statistical pattern is absolutely critical because it became the rulebook for gravity's subsequent work. This rulebook, written in the first instant of time, directly dictated the where and the when of the first starlight. The spectrum of these fluctuations determined the preferred sizes for the first collapsing regions. Certain mass scales became more likely to collapse first, based on the specific amplitude of the density variations imprinted by inflation. It set a rhythm for structure formation, a cosmic timetable where smaller dark matter halos, the minihalos, would form first, providing the nurseries for the very first isolated massive stars. Then, through mergers and accretion, these would build up into larger structures. The pattern was not random. The distribution of those first brilliant points of light across the darkness was a direct reflection of the physics that drove inflation. We can actually see the echo of this pattern today in the cosmic microwave background, the afterglow of the Big Bang, which shows temperature variations that match this predicted statistical signature with stunning precision. The profound implication here is that without inflation's particular and precise tuning, the story of the first stars might never have happened, or it would have unfolded in a completely unrecognizable way. If the quantum fluctuations had been stretched into density variations that were too large, the universe would have been overwhelmingly lumpy. Gravity would have acted too aggressively, potentially collapsing vast regions directly into enormous black holes long before stars could ever form, creating a chaotic and violent cosmos. On the other hand, if the fluctuations had been too small, the universe would have been too smooth. The gentle tug of gravity would have been too weak to gather matter against the relentless expansion of space, resulting in a forever dark, barren, and empty void, a cosmos without form, without stars, and without us. The fact that we exist in a universe filled with galaxies and stars is a powerful testament to the fact that inflation hit a metaphorical Goldilocks zone, producing conditions that were just right for the eventual emergence of structure and life. This explanation, therefore, does more than just describe a mechanism. It roots the spectacular birth of the first stars in the most fundamental and earliest moments of existence, connecting the largest structures we see to the smallest possible scales and the most fundamental laws of physics. But for all the complex interplay of gravity, dark matter, and quantum seeds, the universe still faced one final, immense barrier to star formation, a barrier of light itself. To understand this, we need to step back to a time when the cosmos was not dark at all, but rather a blinding, opaque fog. For the first several 100,000 years after the Big Bang, the universe was far too hot for atoms to exist. It was a searing plasma, a roiling soup of positively charged atomic nuclei and negatively charged electrons, all bathed in an intense, overwhelming bath of light particles or photons. In this chaotic environment, photons couldn't travel more than a tiny distance before slamming into a free electron, scattering off it and changing direction. Light was effectively trapped, bouncing around endlessly in this hot, dense, and blindingly bright prison. This constant interaction between light and matter created a powerful outward radiation pressure, a force that fiercely resisted any attempt by gravity to clump matter together. It was a cosmic standoff, and for eons, radiation pressure was the undisputed winner, preventing gravity from getting started on its work of building structure. This all changed with one of the most pivotal events in cosmic history, recombination. As the universe continued its relentless expansion, it cooled. And around 380,000 years after the Big Bang, the temperature finally dropped to a point where the frantic particles could no longer resist their mutual attraction. Electrons were captured by protons, combining to form the first stable, neutral atoms, primarily hydrogen, with a smaller amount of helium. This process of recombination, which is actually a bit of a misnomer since it was the first time these particles were ever combining, fundamentally altered the nature of the cosmos. With electrons now bound securely inside atoms, the streets of the universe suddenly became much less crowded for light. Photons, which had been constantly bumping into free electrons, now found they could travel vast distances without interruption. In an instant, on a cosmic timescale, the universe went from being opaque to transparent. This moment of liberation for light is what we observe today as the cosmic microwave background radiation. The afterglow of the Big Bang, now cooled and stretched into the microwave part of the spectrum, which fills the entire sky. The implications of this transparency were absolutely profound for the future of star formation. With photons now decoupled from matter and streaming freely across space, the powerful radiation pressure that had been holding gravity at bay simply vanished. For the first time, the universe became a true matter-dominated era. Gravity, which had been waiting in the wings, could finally step onto the stage and take center stage. Without the constant buffeting from radiation, those slight density variations in the neutral hydrogen gas were finally free to respond to their own gravitational pull. The cosmic dark ages could begin not as an era of nothing happening, but as an era of quiet, patient, gravitational gathering. This was the essential thermodynamic milestone that had to be passed. Recombination didn't just make the universe transparent to light. It made the universe transparent to gravity's influence. It removed the last major obstacle, clearing the way for the slow, relentless collapse of gas clouds that would, over millions of years, culminate in the glorious ignition of the very first stars. The timing of this event was exquisitely critical. Had it happened significantly earlier or later, the entire subsequent history of structure formation, and perhaps even the potential for life, could have been drastically different. Now, as we shift our focus from the chaotic turbulence of the early cosmos to the elegant physics governing its collapse, we encounter a principle so fundamental that it underpins the very stability of the universe's largest structures. This is the virial theorem, a powerful concept that describes the beautiful, balanced dance between two competing forms of energy within a gravitationally bound system. Imagine a massive cloud of primordial gas beginning its long collapse. It is brimming with gravitational potential energy, the stored energy it possesses simply by virtue of being gathered together in one place, poised to fall inward. As the collapse begins, this potential energy is converted into motion, into the frenetic kinetic energy of countless atoms rushing toward the center. It might seem like this inward rush would continue unchecked, but the virial theorem reveals a more nuanced and stable outcome. It tells us that for a system to settle into a long-lasting, stable configuration, like a star, it must reach a specific equilibrium where the total kinetic energy of all the moving particles is equal to half the absolute value of its gravitational potential energy. In essence, the energy of motion must precisely balance the energy of position. This equilibrium is the key that prevents a collapsing cloud from either flying apart or catastrophically imploding. Without this balance, a protostellar cloud could have behaved like a spring, collapsing inward so violently that it would rebound and disperse its material back into space, forever thwarting its chance to become a star. Alternatively, it could have continued its unchecked free fall into a point of infinite density. The virial theorem provides the rules for a controlled and sustainable collapse. As the cloud contracts, it heats up, and this increase in thermal pressure provides the outward push that eventually halts the gravitational infall, establishing a harmonious balance. This state of hydrostatic equilibrium is the defining moment when a chaotic cloud becomes a stable, spherical protostar, its immense weight supported by the intense heat and pressure at its core. For the first stars, this principle was absolutely critical in enabling them to grow to such phenomenal sizes. The unique conditions of the early universe, the pristine gas, and the specific cooling mechanisms meant that the clouds collapsing within dark matter minihalos could achieve a particularly efficient energy balance. The virial theorem dictated the final size and stability of these nascent stellar objects. The immense gravitational potential energy of these enormous gas clouds, once converted and balanced, resulted in a correspondingly immense amount of kinetic energy, manifesting as tremendously high temperatures and pressures in the core. This virial balance set the stage for the next act, the ignition of nuclear fusion. Only when the core temperature reached millions of degrees could hydrogen atoms overcome their mutual repulsion and begin to fuse into helium, releasing the torrent of energy that defines a true star. The virial theorem didn't just govern the collapse, it defined the minimum size and mass required for an object to successfully light its nuclear furnace and shine. The reach of this elegant theorem extends far beyond the birth of a single star. It is a cornerstone of astrophysics, applied to understand the stability of entire star clusters, the majestic rotation of galaxies, and even the immense structure of galaxy clusters held together by dark matter. It is a universal law of energy bookkeeping for gravitating systems. In the context of the first stars, it helps explain why they were destined to be giants. The virial condition for a cloud of pure hydrogen and helium, cooling primarily through molecular hydrogen, naturally led to a higher equilibrium temperature and a larger Jeans mass, meaning only the most massive clouds could satisfy the theorem's conditions and achieve a stable configuration. This isn't an obscure piece of mathematical trivia. It is the fundamental reason why the first stars could form at all, and why they took on the magnificent, colossal forms that made them the unforgettable pioneers of the cosmic dawn. While the virial theorem gave us a beautiful principle of balance for stable structures, it doesn't tell us the exact moment a cloud of gas will actually begin its fatal collapse. For that, we need a specific mathematical criterion, a precise rule that separates a stable, drifting cloud from one that is destined to become a star. This brings us to one of the most practical and powerful tools in all of astrophysics, the Jeans instability criteria, named after the British scientist Sir James Jeans. Think of it as the cosmic tipping point, the exact set of conditions under which gravity finally overpowers all other forces and irrevocably takes control. It's the scientific answer to a fundamental question: how big and how dense does a cloud of gas need to be to start forming a star? The genius of the Jeans criterion is that it gives us a formula, a way to calculate a minimum mass and a minimum size, often called the Jeans mass and Jeans length. The concept is elegantly intuitive. Inside any gas cloud, there are two competing forces at play. You have the inward crush of gravity, which is constantly trying to pull everything together. And you have the outward push of pressure, primarily thermal pressure from the gas particles zipping around and colliding with each other, which is trying to keep the cloud puffed up and stable. The gene's instability is the precise moment when the first force definitively wins over the second. It happens when the cloud's self-gravity becomes so strong that the internal pressure can no longer support it against collapse. The formula tells us that this critical point depends on two key properties of the gas: its temperature and its density. A colder cloud will collapse more easily than a hotter one because the particles are moving slower, providing less outward pressure. And a denser cloud will collapse more easily than a sparse one because there's more mass packed into a smaller space, making the gravitational pull much stronger. Now, let's apply this brilliant rule to the unique stage of the early universe. The primordial gas clouds were profoundly different from the star-forming nebulae we see today. First, they were much colder, without any of the complex elements and dust grains that act as super-efficient coolants in modern clouds. The primary cooling mechanism was through molecular hydrogen radiation, which, while effective, could only cool the gas down to a couple hundred degrees Kelvin, much colder than the thousands of degrees seen in later eras. Second, these clouds were likely much denser in their central regions, thanks to the efficient pulling power of the dark matter halos they were nestled within. Plugging these numbers into the gene's formula paints a fascinating picture. The lower temperatures and higher central densities of these first clouds resulted in a significantly lower gene's mass. This means that a much smaller amount of material, a much smaller region within a larger cloud, could suddenly find itself on the wrong side of the stability equation and begin to collapse independently. This had a direct and dramatic impact on the very first generation of stars, known as population Roman III stars. The gene's mass set the fundamental scale for their birth. It determined the minimum mass of a collapsing clump, which in turn heavily influenced the initial mass function, the predicted distribution of star sizes. Because the gene's mass was lower, it allowed for the possibility of fragmentation within a larger cloud. A single, massive cloud of primordial gas could, thanks to turbulence and density variations, break up into several distinct clumps, each one meeting the gene's criterion and collapsing on its own. This is a crucial piece of the puzzle in the long-standing debate about the first stars. For a while, simulations suggested they were all solitary, monstrous behemoths. But the gene's instability, combined with effects like turbulence, helps explain how we might have gotten a wider range of masses, perhaps a few hundred solar mass giants alongside smaller, though still very massive, siblings. The gene's criterion provided the underlying physical rule that made this fragmentation not just possible but probable. Ultimately, the power of the gene's instability is that it gives astrophysicists a predictive tool. By analyzing the temperature and density of a gas cloud anywhere in the universe, whether in the early cosmos or in a modern galaxy, they can calculate its gene's mass and make a strong prediction about its future. Will it remain stable for eons, or is it poised on the brink of a glorious transformation? For the first stars, this mathematical foundation allows us to move beyond mere storytelling and into the realm of quantitative prediction, helping us simulate and understand exactly how those first flickers of light against an infinite darkness came to be. It was the final physical trigger, the last checkbox that needed to be ticked before gravity could officially begin its work of sculpting a cloud of simple gas into the universe's first brilliant engine of creation. Yet even as molecular hydrogen worked its magic, enabling the birth of the first stars, it carried within it the seeds of its own limitation. This humble molecule, so vital for cooling, is also inherently fragile, vulnerable to the very energy that the first stars would soon unleash. This brings us to a powerful cosmic feedback mechanism known as photodissociation, a process where the triumphant birth of one generation of stars could actively hinder the formation of the next. Imagine a single, colossal population 3 star finally igniting within its dark matter minihalo. For millions of years, it burns with ferocious intensity, and its most potent export is not just light, but specifically high-energy ultraviolet photons. These UV photons are like cosmic wrecking balls, traveling out at the speed of light into the surrounding darkness. When one of these energetic photons strikes a molecule of H2, it doesn't just warm it up, it delivers a devastating blow, breaking the chemical bond that holds the 2 hydrogen atoms together and splitting the molecule back into its separate atomic components. This is photodissociation, and its effect on nearby star-forming regions is immediate and dramatic. A cloud of gas that was on the verge of collapse, relying on its molecular hydrogen to efficiently radiate away heat and contract, suddenly finds its primary coolant being systematically destroyed. Without enough H2 molecules, the gas cannot cool effectively. Its internal thermal pressure remains high, and the gravitational collapse that was once imminent grinds to a halt. The cloud stabilizes, entering a kind of suspended animation, unable to proceed down the path to becoming a star. This creates a fascinating self-regulating cycle in the early universe, a feedback loop where star formation in one location actively suppresses star formation in its immediate neighborhood. The first stars essentially carved out vast bubbles of influence around themselves, regions within which the conditions for making new stars were made significantly more difficult. This process began to impose a kind of order and spacing on the emerging cosmic landscape, preventing stars from forming too close together and ensuring that each brilliant pioneer had plenty of room to shine. This narrative, however, contains a crucial and beautiful exception that highlights the unique privilege of the very first stars. The inaugural generation, the true cosmic pioneers, enjoyed a universe that was still entirely pristine and dark. They formed in an environment completely free from this negative feedback. There was no pre-existing background of ultraviolet radiation because no star had ever shone before. Their molecular hydrogen coolant was safe, abundant, and entirely operational, allowing their parent gas clouds to collapse with unimpeded efficiency. This is a key reason why they could grow to such staggering sizes. They were the only stars in all of history to form without any interference from their stellar predecessors. Their birth was a singular, unrepeatable event, possible only during that brief window between the darkness of the cosmic dawn and the moment they themselves flipped the switch and flooded the universe with the first starlight. This delicate dance between creation and destruction, between the molecule that builds and the radiation that breaks, is a profound illustration of a broader principle in cosmic evolution. The universe is not a static stage. It is a dynamic system full of feedback loops where processes often contain their own checks and balances. The same physical phenomenon, the formation of molecular hydrogen, that was absolutely essential for initiating the first star formation, later became a casualty of that very success. This feedback mechanism ensured that star formation did not proceed in an unchecked frenzy, but instead became a more regulated, sustainable process. It connects the life cycle of individual stars to the large-scale evolution of the entire cosmos, showing how the actions of the first luminous objects directly shaped the environment and the rules for all that would follow. The story of photodissociation is ultimately a story of cosmic maturity, marking the transition from the universe's first, unopposed burst of star formation to a more complex, self-regulated era where creation had to contend with the consequences of its own brilliance. But while the steady pull of gravity and the delicate process of cooling set the stage for collapse, the actual birth of a star was far from a serene and orderly event. The nursery for the first stars wasn't a placid pool of gas, it was a chaotic, churning maelstrom. This brings us to a crucial and dynamic explanation for the diversity of the first stellar generation: turbulent fragmentation. Imagine taking a vast cloud of primordial hydrogen and helium and stirring it with an invisible, cosmic spoon at supersonic speeds. Within this swirling chaos, powerful shock waves would ripple through the gas, colliding with each other and creating a complex tapestry of high-density knots and low-density voids. This isn't just random motion, it's a fundamental structuring force. Turbulence acts like a cosmic sculptor, taking a large, monolithic cloud and breaking it apart into smaller, denser fragments, each one a potential seed for a new star. This process of fragmentation is key to understanding why the first stars might not have all been solitary, isolated giants. While the overall conditions of the early universe favored the formation of very massive objects, turbulence introduces a critical element of variety. A single massive cloud of gas, as it begins its global collapse under gravity, could be ripped apart internally by these turbulent motions. Denser regions, strengthened by their own self-gravity, could decouple from the larger flow and begin collapsing independently. Instead of forming one behemoth star at the center, a turbulent cloud could give birth to a small multiple system, a family of massive sibling stars born from the same parent cloud, yet each following its own destiny. The degree and nature of the turbulence within the cloud would directly dictate the outcome: how many fragments form, how massive they are, and how far apart they end up. The source of this early cosmic turbulence is a fascinating puzzle in itself. Some of it was likely primordial, a leftover echo from the violent birth of the universe during the Big Bang, imprinted as faint ripples in the motion of the gas. Another major driver was the dynamic environment of the growing dark matter halos. As these halos merged and collided in the process of hierarchical structure formation, these violent events would have sent powerful shock waves reverberating through the gas within them, stirring it up violently and injecting a tremendous amount of turbulent energy. It's a dynamic feedback loop. Gravity builds the structures that create the turbulence, and that turbulence then shapes how gravity forms stars within those structures. This theory adds a vital layer of realism and complexity to our models. It helps bridge the gap between early simulations that predicted only monstrous, singular stars and more recent, higher-resolution ones that show a wider range of possibilities. Turbulent fragmentation suggests that the first stellar systems could have been more diverse than we once thought, perhaps containing a few stars of 100 solar masses, several of tens of solar masses, and even some failed stars known as brown dwarfs, all born from the same turbulent nursery. This intricate dance between chaos and gravity ensured that the first chapter of star formation was not a simple story of lone giants, but a richer, more varied narrative where the violent beauty of turbulence played an essential role in crafting the first families of light. While the swirling chaos of turbulence and the delicate balance of the virial theorem shaped the local nurseries of the first stars, there was a global, all-pervading presence that set the universal rules for their formation: the cosmic microwave background radiation. This is not some distant or abstract phenomenon. It is the literal afterglow of the Big Bang, cooled and stretched by 13.8 billion years of expansion, and it filled the entire early universe with a soft, uniform glow. For the first stars, this radiation wasn't just a fossil to be studied. It was an active and dominant player in their birth, a pervasive energy field that dictated the very temperature of the cosmos and, by extension, the fate of every collapsing cloud of gas. To understand its power, imagine the universe just a few million years after the Big Bang. Space is dark and mostly empty, but it is far from cold. It is flooded with this background radiation, which at that time was much warmer and more energetic than it is today. Every single atom of hydrogen and helium everywhere in the universe was constantly bathed in this sea of photons. This had a critical effect. It set a universal floor temperature for the gas. No matter how efficiently a gas cloud tried to cool itself through molecular hydrogen radiation, it could never drop below the temperature of this cosmic background radiation. It was like trying to cool a cup of coffee in a room where the air itself was hot. You can only ever get the coffee so cool. This minimum temperature imposed by the CMB created a fundamental physical limit on how cold the primordial gas could get, and this limit had direct and profound consequences for the process of gravitational collapse. The influence of this radiant floor evolved dramatically over time. In the very earliest epochs, when the universe was only 100 million years old or so, the CMB was still relatively warm. This meant the gas couldn't cool to very low temperatures, which kept its internal thermal pressure high. According to the Gaussian instability criteria we discussed earlier, this high-pressure state meant that only the very largest, most massive clouds of gas could overcome this resistance and collapse. The warm CMB effectively acted as a barrier, preventing smaller, less massive regions from forming stars and ensuring that the very first objects to form were likely the true giants. But as the eons passed, the universe continued to expand, and this expansion stretched the wavelengths of the CMB photons, systematically cooling the entire background radiation field. This gradual cooling lowered the universal temperature floor, which in turn allowed the gas to radiate away more of its heat and reach cooler temperatures itself. This slow, cosmic cooling process fundamentally changed the landscape of star formation. As the CMB's temperature dropped, the Gaussian mass, the minimum mass required for a cloud to collapse, also decreased. This meant that progressively smaller and less massive clouds could now cross the threshold of instability. What began as an era that could only produce monstrous, solitary stars gradually transitioned into an era capable of forming stars across a wider range of masses. The CMB didn't just provide a static condition. It provided a dynamically changing environment that guided the evolution of star formation itself. Its relentless cooling over millions of years slowly democratized the process, eventually allowing for the smaller, longer-lived stars that would become the building blocks of future galaxies and planetary systems. This explanation provides a breathtakingly direct link between the largest scales of the cosmos and the birth of individual stars. The CMB is our most precise window into the conditions of the infant universe, and its properties are imprinted on the formation history of the very first luminous objects. The temperature variations we see in the CMB map today are the fingerprints of the density variations that would later grow into galaxies. But its role was far more active than that of a simple blueprint. It was a universal thermostat, governing the thermal state of all gas and presiding over the timing and the scale of the cosmos's first great transformation from darkness into light. The afterglow of creation didn't just illuminate the universe, it actively engineered the conditions that made starlight possible. To truly appreciate the uniqueness of the first stars, we must imagine a universe not just without light but without dirt. In the context of astrophysics, metals refer to any element heavier than helium, carbon, oxygen, iron, all the fundamental building blocks of planets and life. The early cosmos had none of it. It was a place of stunning chemical purity, a vast expanse composed of only 75% hydrogen, 25% helium, and a trace whisper of lithium. This pristine, zero metallicity environment wasn't just a minor detail. It was the single most important factor that dictated the fate of the universe's first stellar generation, forcing them down an evolutionary path so extreme that it has no modern parallel. This profound lack of heavier elements completely rewrote the rulebook for star formation. In today's universe, the nebulas where stars are born are filled with microscopic dust grains and complex molecules rich in elements like carbon and oxygen. These tiny particles are incredibly efficient at radiating away heat. They act like a sophisticated cosmic air conditioning system, allowing a giant molecular cloud to cool down rapidly, shed its thermal energy, and fragment into dozens or even hundreds of smaller, denser clumps. This is why we see stars being born in large clusters with a wide range of masses, from red dwarfs a tenth the size of our Sun to brilliant blue giants. But in the primordial universe, that entire cooling mechanism was simply absent. There was no dust, no soot, no complex carbon monoxide molecules to efficiently radiate away the intense heat generated by gravitational collapse. The only coolant available was the fragile molecular hydrogen we discussed earlier, and while it was effective, it was far less powerful than metal-based cooling. This limitation had a dramatic and direct consequence. It kept the gas warm. As a massive cloud of pure hydrogen and helium collapsed under its own weight, the energy from that infall was converted into heat, causing temperatures to soar. Without efficient metal coolants, this heat couldn't be quickly dissipated. The gas remained at a significantly higher temperature and pressure throughout the collapse process than it would in a modern nebula. And this thermal state is the key that unlocks the mystery of their immense size. Remember, the genes mass the minimum mass required for a cloud to collapse. That critical value is directly proportional to the temperature of the gas. Hotter gas has higher internal pressure, which fiercely resists gravitational collapse. To overcome this stronger pressure, a cloud needed to be much more massive. It needed a far greater gravitational pull to win the tug of war against its own heat. Therefore, the zero metallicity environment, by keeping the gas hot, automatically selected for only the largest possible gas clouds to successfully form stars, filtering out any smaller, less massive regions that might have otherwise created sun-sized stars. The result was a population of stellar titans, known as population 3 stars, that are almost unimaginable to us today. Current models suggest these pioneers routinely reached masses between 100 and 300 times that of our Sun, with some theories allowing for even larger behemoths. Their physical properties were as extreme as their size. They would have burned at searing surface temperatures, shining with a ferocious bluish-white light that was millions of times more luminous than our Sun. Their cores, squeezed by unimaginable gravity, would have fused hydrogen into helium at a frantic, unsustainable rate. This profligate spending of their nuclear fuel meant their lives were spectacularly brief. Where a star like our Sun will burn steadily for 10 billion years, these colossal giants lived fast and died young, exhausting their fuel in just a few million years before meeting a violent end in cataclysmic supernova or even directly collapsing into black holes. This unique chemistry-driven narrative does more than just explain size. It connects the first stars directly to our own existence. Their short, brilliant lives and violent deaths were the universe's first and most important act of alchemy. It was within their furnaces and in the unimaginable blasts of their supernova that the first heavy elements were forged: the carbon in our cells, the oxygen we breathe, the iron in our blood. They took a pristine universe and polluted it with the essential ingredients for everything that was to come: rocks, oceans, planets, and life. The zero metallicity condition was a one-time state, a unique chapter that closed as soon as the first stars finished their work. Every star that has formed since, including our Sun, was born from gas enriched by those first giants, forever changing the rules of star formation and setting the stage for a universe rich with complexity and possibility. While the serene collapse of an isolated gas cloud could form a single, massive star, the universe's larger narrative was one of relentless, violent construction. The dark matter halos that cradled the first stars were not static structures. They were dynamic islands adrift in an expanding sea, destined to collide and merge in a spectacular display of cosmic architecture. These mergers between dark matter halos were far more than simple collisions. They were transformative events that violently reshaped the gas within them, funneling it into dense, chaotic maelstroms that became the ultimate catalysts for starlight. This process of hierarchical growth, building large structures from the merger of smaller ones, didn't just provide more mass. It created the specific, violent conditions necessary to overcome one of the most stubborn obstacles in astrophysics: angular momentum. Every cloud of gas in the universe has some inherent spin, a legacy of the tidal forces from surrounding structures and the residual motion from the Big Bang itself. As a cloud collapses under gravity, this spin amplifies dramatically, much like a figure skater pulling in their arms to spin faster. This creates a powerful centrifugal force that pushes outward, resisting further gravitational collapse and often causing the gas to settle into a vast, rotationally supported disk. For a star to form, this rotational energy must be dissipated. The gas must find a way to lose its angular momentum so that material can continue to fall inward to the core. In isolated minihalos, this process was slow and inefficient, often limiting the rate at which a protostar could gather mass. But during a merger, all bets were off. The violent gravitational interaction between two halos acted like a cosmic blender, violently stirring the gas within them. This chaotic turbulence created shocks, compression waves, and gravitational torques that were incredibly effective at transferring angular momentum outward, allowing gas to lose its spin and fall precipitously toward the center of the new, combined halo. The result was a massive inflow of gas into the very heart of the merger. Imagine two vast, invisible clouds of dark matter passing through one another, their gravitational pull dragging the visible gas along for a tumultuous ride. The gas clouds from both halos were slammed together, their kinetic energy converted almost instantly into intense heat and pressure. This created incredibly dense, shocked regions where the local gas density could spike by orders of magnitude in a very short time. It was in these chaotic, high-pressure environments that the critical thresholds for gravitational collapse were not just met, but were dramatically exceeded. The merger provided a powerful kickstart to star formation, compressing gas that might have lingered for millions more years into a state where collapse was immediate and violent. These events likely triggered intense, explosive bursts of star formation, creating not just single stars, but the first tightly bound clusters of stellar siblings. This relentless cycle of merger and assembly is the core of the hierarchical model of structure formation. The first tiny minihalos, each potentially hosting a single massive star, were the universe's fundamental building blocks. Gravity drew them together, assembling them into larger and larger structures, first into dwarf galaxies, and eventually into the majestic spirals and ellipticals we see today. Each major merger event funneled fresh, cold gas into the growing structure, providing the fuel for new generations of stars. This process also built up the total mass of the dark matter halo, which was crucial for efficient cooling. Larger halos had deeper gravitational potential wells, which could hold onto hotter gas and allow it to cool and condense over longer timescales. Furthermore, The increased pressure in these larger systems encouraged the gas to fragment more readily, potentially leading to a wider range of stellar masses in subsequent generations compared to the first solitary giants. Framing the birth of stars within this context of cosmic construction completely changes our perspective. A star is not just an isolated object, it is a product of its environment, its formation often triggered by the large-scale assembly of the universe itself. The distribution of the first stars across the sky, the timing of their ignition, and their eventual grouping into larger galaxies were all direct consequences of this bottom-up building process. The dark matter, invisible and elusive, was the master architect, its gravitational pull orchestrating the collisions that would forge the visible universe. The mergers of its halos were the cosmic construction sites where the violence of creation provided the necessary conditions to turn spinning clouds of pristine gas into the brilliant, lasting beacons that ended the universe's dark age. Yet for all the grand architecture of dark matter and the sweeping forces of gravity, the actual ability of a gas cloud to collapse and form a star came down to events on an almost unimaginably small scale. This brings us to the delicate and intricate world of primordial gas chemistry, where the fate of the entire cosmos hinged on the behavior of a few simple atoms and the fragile molecules they could form. In a universe devoid of the complex elements we take for granted, the only players on the chemical stage were hydrogen, helium, and a minuscule amount of lithium. Their interactions, though limited, had to perform a miracle. They had to find a way to allow a massive cloud of gas to shed the immense heat generated by its own gravitational collapse. Without an efficient cooling mechanism, that heat would create overwhelming pressure, forever preventing the cloud from condensing into a star. The universe's solution was elegant in its simplicity, crafting the first coolants from the only ingredients available. The most important of these by far was molecular hydrogen, or H2. Forming this molecule in the early universe was no simple task. With no solid surfaces like dust grains to act as a meeting place, the two hydrogen atoms had to come together in a precise three-body collision, an event that was incredibly rare in the diffuse primordial gas. The process often required a facilitator. A free electron, for example, could briefly attach to a hydrogen atom, forming a negative ion. This gave the atom a slightly larger effective size, increasing its chance of colliding with another hydrogen atom and allowing them to form a stable bond, releasing the electron back into the wild to start the process again. It was a slow, inefficient dance, but over millions of years, trace amounts of this vital molecule began to accumulate within the collapsing clouds, and H2 had a special talent. Its structure allows it to vibrate and rotate in specific ways. When it collides with another atom, it can absorb kinetic energy, essentially heat, and then release that energy by emitting a low-energy infrared photon. This photon could then travel straight out of the gas cloud, carrying the unwanted thermal energy with it into the void of space. This was the critical release valve for the first stars. But molecular hydrogen wasn't the only molecule on the cosmic menu. Theorists have long speculated that lithium hydride, or Li-H, formed from the reaction of lithium atoms with hydrogen atoms, could have played a supporting role. Lithium was only present in vanishingly small quantities, a relic of the first few minutes of the Big Bang, but it has unique properties. The Li-H molecule is highly polar, meaning it has a distinct positive and negative end, which makes it very effective at radiating away energy through rotational transitions. In the coldest, densest inner regions of a collapsing cloud, where temperatures might have dipped low enough for lithium to play a part, Li-H could have provided an additional, specialized cooling channel. Its impact was likely minor compared to the overwhelming effect of H2. but its potential presence highlights the universe's remarkable ingenuity, exploring every possible chemical pathway to achieve its goal. Understanding this microphysics is not just academic, it directly dictated the macro-scale outcome of star formation. The efficiency of this cooling determined how low the gas temperature could fall, which in turn set the gene's mass, the minimum mass required for a cloud to collapse. The limited cooling power of H2 meant the gas remained relatively warm, which favored the formation of very massive objects. This simple chemistry is the fundamental reason we believe the first stars were giants. Furthermore, these chemical reactions were highly sensitive to their environment. The faintest whisper of ultraviolet radiation from a nearby star could easily break apart these delicate molecules in a process called photodissociation, stripping a cloud of its ability to cool and halting star formation in its tracks. This underscores the privileged position of the very first stars. They formed in a silent, dark universe, free from this disruptive feedback, their chemical factories operating undisturbed. The birth of light, therefore, was not just a story of gravity's pull, but a testament to the universe's ability to engineer a solution from the most basic atomic parts, using simple chemistry to orchestrate its most spectacular transformation. But as these vast clouds of gas began their gravitational descent, they carried with them a hidden property that threatened to stall the entire process before it could even truly begin: spin. Every structure in the universe, from a swirling galaxy to a collapsing gas cloud, inherits a certain amount of rotation from the turbulent motions of the cosmos and the tidal pulls of its neighbors. This inherent spin translates into angular momentum, a fundamental property of physics that describes an object's resistance to changes in its rotation. For a forming star, this rotational energy is a formidable obstacle. Imagine a vast cloud of primordial gas, hundreds of light years across, beginning to shrink under its own weight. As it contracts, its spin accelerates dramatically, just like a figure skater pulling their arms in to spin faster. This creates a powerful centrifugal force that pushes outward, fiercely resisting the inward crush of gravity. Without a way to shed this spin, the cloud could never collapse into a dense star. Instead, it would flatten into a stable, spinning disk, perhaps eventually fragmenting into a multiple star system, or simply lingering as a failed, disk-like structure. For the first stars to form, this rotational energy had to be transported away from the central region, allowing material to continue its journey inward. The early universe, lacking the complex physics of later eras, had to rely on a few fundamental mechanisms to solve this angular momentum problem. One of the most promising candidates is a process known as magnetic braking. Even if the primordial magnetic fields were incredibly weak, as we discussed earlier, they could have played an outsized role here. A partially ionized gas cloud, one where some atoms have been stripped of their electrons, is a conductor. As this cloud rotates, its magnetic field lines are effectively frozen into it. These field lines can act like anchors, extending out into the thinner, surrounding material. The inner, faster rotating parts of the cloud try to drag these field lines with them, but the outer, slower moving material provides resistance. This interaction creates a torque, a twisting force, that effectively transfers angular momentum from the fast-spinning inner regions to the slower outer regions. It's a cosmic braking system, using magnetism to slow the central spin and allow the core to continue contracting. This process could have been crucial for allowing a single, massive object to form at the heart of the cloud rather than a fragmented binary system. Another potential mechanism involves the chaotic, viscous forces within the turbulent gas itself. The early star-forming clouds were not serene, smooth spheres. They were filled with supersonic turbulence, shock waves, and chaotic motions. This internal chaos can act as a form of friction, allowing different parts of the cloud to transfer momentum between them. Dense, fast-rotating clumps could collide with slower-moving material, effectively passing off their spin in these violent interactions. Furthermore, gravitational instabilities within a forming disk can create spiral waves density patterns that act like gravitational levers, pulling angular momentum outward and allowing mass to drift inward. These processes are less about a single, elegant solution and more about the complex, messy dynamics of a collapsing system finding ways to redistribute its energy through sheer turbulence and gravitational interaction. The efficiency of this angular momentum transport was absolutely critical in determining the final outcome. If it was too inefficient, the cloud would indeed fragment into a multiple system of smaller stars as the disk broke apart. If it was highly efficient, it could funnel a tremendous amount of material onto a single, growing core at the center, leading to the formation of a true stellar behemoth. This adds a vital layer of nuance to our understanding of the first stars. It suggests that their final masses weren't solely determined by the initial size of their parent cloud or the efficiency of cooling, but also by the intricate and often unpredictable dynamics of how that cloud managed its own spin. The transport of angular momentum was the final, crucial piece of engineering required to overcome the last major physical barrier to star formation, transforming a spinning disk of potential into a brilliant, spherical engine of nuclear fusion. However, the influence of these brilliant pioneers did not end with their destructive ultraviolet radiation. In fact, their most profound legacy was written in the complex and beautiful cycles of creation and destruction that unfolded in their immediate surroundings. When a massive first star finally ignited, its flood of high-energy photons did more than just dissociate molecules. It began to violently tear electrons from their host atoms in a process known as ionization. The star essentially carved out a vast bubble around itself, a region called an H-II region, where the hydrogen gas was heated to tens of thousands of degrees and stripped down to a searing, ionized plasma. This expanding sphere of light and heat pushed against the surrounding neutral hydrogen like a cosmic plow, sweeping it up into a dense, cool shell at its outer edge. For a time, star formation within this ionized bubble was utterly impossible. The gas was too hot and too turbulent to collapse. But the story takes a fascinating turn when we consider the eventual fate of these magnificent, short-lived stars. After a mere 2 or 3 million years, a cosmic blink of an eye, they exhausted their nuclear fuel and met a cataclysmic end in a supernova explosion. The sudden disappearance of the primary source of ionizing radiation was a dramatic event. Without the constant barrage of ultraviolet photons to keep it ionized, the gas within the huge H-II region began to cool. Electrons, no longer being violently stripped away, started to slow down and recapture their protons, peacefully recombining into neutral hydrogen atoms once more. This process of recombination is not a quiet one. It releases energy, but more importantly, it allows the gas to cool down dramatically and increase in density. The once hot, puffy plasma was now transforming back into a cold, dense, and neutral medium, but with a crucial difference: it was now compressed into a thick, massive shell by the earlier expansion of the ionized bubble. It is within these cool, dense shells of reborn gas that the universe found the ingredients for its second act. The immense pressure and density within these swept-up layers created conditions that were ripe for a new wave of gravitational collapse. The very same radiation that had initially suppressed star formation now, in its absence, indirectly created the perfect nurseries for the next generation. Regions within these shells could become gravitationally unstable, fragmenting and collapsing to form new stars. This second generation of stars, however, was fundamentally different from the first. They formed from gas that had been enriched by the supernova ejecta of their massive progenitors, gas now sprinkled with the first heavy elements like carbon, oxygen, and iron forged in the heart of the first star and blasted out in its death throes. This metallicity, however slight, introduced more efficient cooling processes, allowing these new stars to form with a wider range of masses, including smaller, longer-lived stars much like our own Sun. This creates a breathtaking feedback loop, a cosmic cycle of death and rebirth where the end of one stellar generation directly catalyzes the beginning of the next. The first stars were not just lonely giants, they were the architects of their own succession. Through the powerful mechanism of ionization and recombination, they sculpted their environments, first clearing space around themselves and then, in their dramatic departure, leaving behind the compressed raw materials for their successors. This explanation beautifully illustrates how the universe leverages its own processes, creating a complex interplay where the intense light of the first stars doesn't just illuminate the cosmos, but actively engineers the conditions for its own fertile and ongoing evolution, seeding the universe with the potential for future diversity and complexity. To grasp the profound impact of these primordial waves, we must first reimagine the infant universe not as a silent void, but as a roaring sea of sound. In the first few 100,000 years after the Big Bang, the cosmos was a dense, seething plasma, a tightly coupled fluid of light and matter. Within this hot, pressurized medium, any slight disturbance would have propagated outward as a pressure wave, a literal sound wave moving at a significant fraction of the speed of light. These weren't gentle ripples, they were colossal tsunamis of compression and rarefaction, racing across the expanding universe. Their origin is tied directly to the gravitational tug of war that played out on a cosmic scale. A region of slightly higher density would have a stronger gravitational pull, drawing in surrounding material. But as this material rushed inward, it increased the pressure and temperature in the dense region, causing it to rebound and push outward again. This created a continuous cycle of collapse and rebound, setting up a series of oscillating waves that rang through the primordial plasma like a struck bell. The fate of these acoustic oscillations was sealed when the universe underwent recombination. The moment electrons and protons combined to form neutral atoms, the photons were set free and the universe became transparent. This act of decoupling had a stunning effect on the sound waves. It froze them in place. Imagine a wave traveling across the surface of a pond that suddenly, instantly turns to ice, preserving the wave's shape for all time. In the exact same way, the pattern of those pressure waves, the regions of peak compression and maximum rarefaction, was imprinted permanently onto the distribution of matter. The slightly denser regions, the crests of these frozen waves, became the preferred sites for matter to accumulate. They were the universe's first resonant structures, and their scale was not random. The fundamental wavelength was determined by how far a sound wave could travel from the Big Bang until the moment of decoupling. This distance, known as the sound horizon, became a fundamental ruler etched across the entire sky. We can still see the ghostly imprint of this cosmic music today in the detailed maps of the cosmic microwave background. The subtle variations in the CMB's temperature are not random noise. They form a precise power spectrum with a series of peaks and troughs. The first peak corresponds to the fundamental wavelength, the sound horizon at the time of decoupling. The subsequent peaks are harmonics, much like the overtones of a musical instrument, revealing the physics of the early universe with incredible precision. This pattern is the direct fossil record of those standing density waves, and it tells us the preferred scales at which matter began to clump together. This means the distribution of the first star-forming clouds was not arbitrary. It followed a distinct periodic pattern with a statistical preference for clouds separated by a specific distance scale, that of the sound horizon. This explanation provides a breathtakingly elegant link between the largest scales of the cosmos and the birth of the very first stars. The acoustic oscillations set up a resonant grid, a cosmic architecture that guided where the first structures would be most likely to form. The wavelength of these waves determined the mass scale of the first collapsing regions, directly influencing the potential size of the dark matter minihalos that would serve as stellar nurseries. It means the first points of light did not ignite in a random scattering, but in a pattern that echoed the fundamental music of the Big Bang itself. The birth of the first stars was, in a very real sense, the universe listening to its own earliest vibrations and responding by gathering matter at the resonant nodes of its own frozen song, turning sound into the first solid structures and ultimately into light. While the grand dance of gravity and the intricate chemistry of molecular cooling set the broad stage for star formation, the actual process of turning a diffuse cloud into a dense stellar core was governed by the relentless laws of thermodynamics. This brings us to a powerful and often overlooked driver of structure, thermal instability. Imagine a vast, mostly uniform cloud of primordial gas. It isn't perfect. Some regions are a fraction of a degree cooler than others, and some are ever so slightly denser. In the delicate thermal balance of the early universe, these tiny differences were enough to trigger a runaway process. A slightly cooler patch of gas has lower internal pressure. In the constant push and pull between thermal pressure pushing out and gravity pulling in, this cooler region suddenly finds itself at a disadvantage. The surrounding, warmer gas with its higher pressure can effectively squeeze it. This compression causes the already cool, dense region to become even denser and, crucially, even cooler. Why? Because as it compresses, its ability to radiate energy through molecular hydrogen cooling becomes more efficient. It's a powerful positive feedback loop. Cool and dense leads to better cooling, which makes it even cooler and denser, which allows it to cool even further. This process causes the cloud to effectively splinter, with cold, dense knots condensing out of the warmer, more diffuse background medium like droplets of water, forming in a saturated cloud of steam. These condensing droplets didn't just form in isolation, they became the gravitational seeds for the next act. Once a region underwent this thermal fragmentation and reached a high enough density, its own self-gravity became significant. The thermal instability effectively did the preliminary work, creating the localized overdensities that gravity could then seize upon and amplify. Gravity and thermodynamics worked in a powerful tandem. Thermal instability created the initial fragments, and gravity finished the job, pulling each fragment inward into a runaway collapse. This partnership was essential for breaking up a massive, monolithic cloud into multiple star-forming cores. Without this process, a cloud might have collapsed as a single, sluggish entity, potentially forming one unimaginably large star. Instead, thermal instability helped to foster the formation of multiple objects within a single nursery, perhaps explaining how the first stellar systems could contain several massive stars born from the same parent cloud. The unique environment of the early universe made this process particularly potent. The absence of dust and metals meant that the gas had a very specific and limited way to cool. Its thermal behavior was exquisitely sensitive to the presence and efficiency of molecular hydrogen. In a modern cloud, dust provides a stable, robust cooling channel that operates across a wide range of temperatures and densities, which can smooth out these instabilities. But in the primordial world, the cooling was entirely dependent on the fragile H2 molecule. This made the entire system more volatile and prone to sudden phase changes. A small change in density could dramatically increase the H2 formation rate, leading to a sharp increase in cooling efficiency and triggering a rapid transition from a warm, stable state to a cold, collapsing one. This sensitivity meant that thermal instability could arise suddenly and locally, creating a patchwork of different conditions within a single cloud and leading to a more diverse array of collapsing cores than if the process had been more uniform. It was thermodynamics operating on a knife's edge, where slight variations could determine the fate of vast reservoirs of gas, pushing them over the threshold from quiet potential into the violent act of creation. Yet for all the grand, overarching laws of physics we've explored, from the resonant echoes of primordial sound waves to the delicate balance of thermal instabilities, the universe's transition to light was not a uniform, synchronized event. It was a patchwork, a tapestry of first dawns emerging at different times and in different places, each one a unique and local phenomenon. This brings us to a concept that embraces the beautiful randomness woven into the fabric of reality itself: cosmic variance. The initial conditions of the universe, imprinted by inflation, were not a perfectly smooth and identical template applied everywhere. While the statistical pattern of those quantum fluctuations was uniform, their specific, local manifestation was not. Imagine a vast, calm ocean viewed from high above. Its average wave height might be consistent, but if you look closely at any given square mile, the precise arrangement of waves and troughs is utterly unique. This is the essence of cosmic variance, the inherent scatter and randomness in how those initial density, temperature, and velocity fluctuations were distributed from one region of space to another. This randomness had profound consequences for the timeline of cosmic dawn. While the average time for the first star to form in the universe might have been around 200 million years after the Big Bang, this was just an average. Some exceptionally fortunate regions, blessed with a slightly higher concentration of those initial overdensities, would have crossed the threshold for collapse much earlier. In these lucky patches, the gravitational tug-of-war would have been won sooner, allowing massive clouds to condense and ignite their nuclear furnaces while the rest of the cosmos was still shrouded in darkness. Conversely, other, less fortunate regions, those that started out just a little bit smoother and more diffuse, would have had to wait longer. Their gravity would have had to work more patiently to gather enough material, delaying their first starlight by tens of millions of years. This means the end of the Dark Ages was not a single, universe-wide flip of a switch, but a gradual dawning with isolated points of light flickering on one by one across the infinite blackness, each one a testament to the unique initial conditions of its local neighborhood. We see this elegant chaos reflected powerfully in the most sophisticated supercomputer simulations of the early universe. When astronomers run these digital experiments, they don't get a single, definitive answer. Instead, they get a range of outcomes, a distribution of possibilities. One simulation might show the first star igniting at a redshift of 30, while another, with slightly different initial random seeds, might show it at 25. Some simulated volumes will contain several massive stars, while others, of exactly the same size, might contain only one or even none at all. This scatter isn't a flaw in the models, it's their greatest strength. It accurately captures the fundamental randomness that was built into the universe at its birth. The observed heterogeneity in these simulations isn't an error to be smoothed over. It is the precise effect we would expect to see if our understanding of cosmic variance is correct. It teaches us that to understand the first stars, we must think not in terms of certainty, but in terms of probability and distribution. This explanation does more than just account for differences in timing. it helps us understand the potential diversity of the first stellar populations themselves. A region that started with a particularly high degree of turbulence might have fragmented into a small cluster of massive stars. A neighboring region that began with a smoother, more monolithic cloud might have produced a single, isolated behemoth. The specific initial velocity fields in one area could have led to faster accretion rates and more massive objects, while in another, different flow patterns could have resulted in a different outcome. Cosmic variance embraces this randomness, recognizing it not as noise, but as an essential feature of a universe that began with quantum mechanical fluctuations. It tells us that the first stars were not a monolithic population of identical giants, but a diverse first generation, their properties as varied and unique as the particular cosmic lottery ticket of their initial conditions. This inherent scatter is the universe reminding us that from its very first moments, it has valued individuality and chance, weaving a story of creation that is not predetermined, but rich with possibility and local flavor. Up until now, we've largely thought of the universe's initial conditions as following a very specific, predictable statistical pattern, a nearly perfect Gaussian distribution of those tiny quantum fluctuations. But what if the early universe wasn't quite so orderly? What if its opening moments contained subtle statistical anomalies, tiny deviations from this perfect randomness that created unexpected cosmic outliers? This possibility leads us to one of the most profound and cutting-edge explanations for the first stars, the potential role of primordial non-Gaussianities. In simple terms, Gaussian statistics describe a familiar bell curve where most things are average, extreme events are very rare, and the distribution is perfectly symmetrical. This is the standard prediction of simple inflationary models, but if the physics of inflation were more complex, it could have imprinted slight deviations into this pattern statistical wrinkles that made the universe slightly more likely to produce rare, extreme events. In the context of the cosmic dawn, this would mean that amidst the general sea of gentle density variations, there could have been a few regions that were not just slightly denser, but were true statistical monsters, exceptionally rare, massive overdensities that stood out dramatically from the crowd. The impact of such a statistical anomaly would have been immediate and dramatic for star formation. A region blessed or perhaps cursed with a strong positive non-Gaussianity wouldn't have had to wait for the slow, patient work of gravitational amplification. Its initial head start would have been so enormous that its gravitational collapse could have begun significantly earlier than anywhere else in the universe. This would have created a population of truly precocious stars, igniting their furnaces tens of millions of years before their more statistically average neighbors. Furthermore, the sheer intensity of these initial overdensities could have led to the formation of the most massive stars imaginable, objects pushing the very upper limits of what is physically possible, perhaps even the hypothetical supermassive stars that some theorists have proposed. These wouldn't just be the first stars, they would be the first anomalies, their existence a direct challenge to our standard models, and a potential window into the highest energy physics that shaped reality itself. The hunt for evidence of these non-Gaussianities is now one of the most active frontiers in cosmology, precisely because it connects the macroscopic world of the first stars directly to the microscopic physics of inflation. The distribution of the first galaxies and stars across the sky is not just a random scattering, it is a fossilized map of those initial density fluctuations. If that map shows an unexpected number of extremely bright, extremely early stellar systems clustered together in specific ways, it could be the signature we're looking for. Astronomers are using powerful telescopes like the James Webb Space Telescope to peer back to the very edge of the observable universe, not just to see the first lights, but to carefully count them, map their positions, and measure their properties, searching for any statistical oddity that might betray a non-Gaussian origin. It's a cosmic detective story where the clue is an improbable arrangement of ancient suns. This explanation elevates the narrative of the first stars from a tale of inevitable physical processes to a potential test of our most fundamental theories. The presence or absence of primordial non-Gaussianities can help us distinguish between different models of inflation, telling us whether the universe's exponential expansion was driven by a single, simple field or by a more complex interplay of energies. It connects the birth of a star in the Dark Ages to the quantum gravity regime, where space-time itself may have behaved differently. The first stars, therefore, become more than just ancient celestial objects. They become cosmic probes, their very distribution and timing serving as a messenger from the first fraction of a second of time, carrying information about the laws of physics at energies we can never hope to recreate in a laboratory. Their light, after traveling for over 13 billion years, may finally answer the question of whether the infant universe was a place of perfect statistical order, or if it was born with a few fascinating imperfections written into its initial conditions. While the initial gravitational collapse of a gas cloud was a pivotal moment, it was far from the end of the story for a growing protostar. The birth of the first stars wasn't a single, discrete event but a dynamic, ongoing process of construction, fueled by a continuous rain of fresh material from the surrounding cosmos. This brings us to the vital role of gas infall and accretion rates, the relentless delivery of fuel that determined whether a nascent star would become a modest giant or a true cosmic titan. Imagine a newly formed protostar at the heart of its dark matter halo. It has just begun to shine, its gravity having drawn in enough material to ignite fusion at its core. But the reservoir of gas from which it formed is not yet exhausted. Far from it. From the vast filamentary structure of the cosmic web and the outer reaches of the halo itself, a continuous stream of cold, pristine hydrogen and helium continues to flow inward, drawn by the deepening gravitational well. This isn't a gentle drizzle. It's a massive, ongoing infall of material that provides a sustained source of fuel for the young star, allowing it to keep growing in mass long after its initial formation. The rate at which this gas was delivered, the accretion rate, was arguably just as important as the initial conditions of the cloud itself. In the early universe, these rates were likely staggering, orders of magnitude higher than what we observe in star-forming regions today. Simulations suggest that gas could have cascaded onto the central protostar at a rate of up to 1 solar mass every 10,000 years. At this incredible pace, a star could balloon from a mere 10 solar masses to 100 in less than 1,000,000 years. This high-rate, sustained accretion helps explain how the first stars could overcome a major physical barrier. As a star grows more massive, it shines more brightly, and its intense radiation exerts a powerful outward pressure on the surrounding gas, potentially halting further infall and limiting its final size. This is a form of feedback, but if the accretion rate is high enough, if the gas is falling in so rapidly and with such density that it can effectively shield itself from the star's radiation, this feedback can be overwhelmed. The star's own brilliance is essentially smothered by the sheer volume of incoming material, allowing it to continue growing to truly monstrous proportions. This environment of rapid, competitive infall leads to a fascinating and dynamic scenario known as competitive accretion. In a crowded stellar nursery where multiple protostars are forming from the same gas reservoir, they aren't just passively collecting material, they are actively competing for it. Each star's gravitational pull is vying for a share of the incoming gas. In this cosmic free-for-all, the rich get richer, A protostar that gains a slight initial mass advantage will develop a slightly stronger gravitational pull, allowing it to attract and capture a disproportionate share of the available gas. This allows it to grow even larger, further increasing its gravitational dominance in a powerful feedback loop. Meanwhile, its smaller siblings are starved of fuel, their growth stunted. This process could naturally produce a wide range of stellar masses within a single system, from a few dominant behemoths that gorge on the majority of the gas down to many smaller, less massive objects that managed to form but were ultimately outcompeted for the remaining resources. This explanation fundamentally reframes our view of the first stars from static objects to dynamic systems. Their formation wasn't a simple case of a cloud collapsing and then fusion turning on. It was a prolonged, chaotic, and highly competitive battle for mass, governed by the complex interplay between gravity, radiation, and the relentless flow of gas from the larger cosmic environment. The final mass of a population 3 star was not just a product of the initial size of its parent cloud, but a testament to its ability to continuously draw in material from its surroundings and win the battle against its own brilliant but self-limiting radiation. It was a race between growth and self-destruction, and in the dense, gas-rich environments of the first minihalos, growth often won, creating the legendary giants that first illuminated the universe. But as these vast clouds of pristine gas swirled inward, driven by the relentless pull of gravity, they carried with them a hidden property that threatened to halt the entire process before a star could even form: spin. Every structure in the cosmos inherits some amount of rotation, a legacy of the turbulent motions within the gas and the tidal pulls from neighboring dark matter halos. This inherent spin translates into angular momentum, a fundamental property of physics that describes an object's resistance to changes in its rotation. For a collapsing cloud, this rotational energy is a formidable obstacle. As the cloud contracts, its spin accelerates dramatically, just like a figure skater pulling their arms in to spin faster. This creates a powerful centrifugal force that pushes outward, fiercely resisting the inward crush of gravity. Without a way to shed this spin, the cloud could never collapse into a dense star. Instead, it would flatten into a stable, spinning disk, perhaps eventually fragmenting into a multiple star system or simply lingering as a failed structure. The early universe, lacking the complex physics of later eras, needed a fundamental mechanism to solve this problem, and it may have found one in the subtle but persistent force of primordial magnetic braking. This concept hinges on the potential existence of faint magnetic fields woven into the fabric of the infant cosmos. Even if these fields were incredibly weak, billions of times weaker than Earth's magnetic field, they could have played an outsized role in the dynamics of collapse. The key lies in the behavior of a partially ionized gas. While the universe was mostly neutral after recombination, it wasn't perfectly so. Collisions and the faint background radiation could still knock electrons loose from their atoms, creating a sparse population of charged particles. This made the gas a slight electrical conductor. As this weakly ionized cloud rotated, its charged particles became tied to the magnetic field lines, effectively freezing the field into the gas. These magnetic field lines could then act like long, invisible levers or anchors, extending out from the fast-spinning inner regions of the cloud into the slower-moving outer material or even the surrounding void. Here's where the braking effect occurs. The inner, rapidly rotating part of the cloud tries to drag these magnetic field lines with it as it spins. However, the outer material provides resistance, creating a tension in the field lines. This tension generates a torque, a twisting force that acts to slow down the spin of the inner material while simultaneously speeding up the outer material. It's a cosmic transaction where angular momentum is transferred from the center to the outskirts. This process allows the central core to lose its spin, overcome the centrifugal barrier, and continue its gravitational contraction. Think of it like a spinning ice skater extending their arms to slow down. The magnetic fields provide the outward extension that allows the inner core to break its rotation and pull itself closer together. This mechanism would have been particularly crucial in the pristine early universe, where other common methods for shedding angular momentum like gravitational interactions with other stars or the viscous forces in a dusty disk simply didn't exist yet. The effectiveness of this entire process wasn't guaranteed. It depended critically on two factors: the strength and the geometry of these primordial magnetic fields. If the fields were too weak, their leverage would have been insignificant, and they would have been easily twisted and tangled by the gas motions without producing a meaningful braking effect. Their geometry was equally important. A well-ordered, large-scale field threading through the cloud would be far more effective at transferring momentum over long distances than a chaotic, tangled mess of small magnetic loops. The specific alignment of the field lines relative to the cloud's axis of rotation would determine exactly how the torque was applied and how efficiently the spin was dissipated. This means that the success of star formation in different regions of the early universe could have been a lottery, influenced not just by density and temperature, but by the invisible and mysterious magnetic architecture inherited from the universe's birth. This explanation adds a layer of exquisite complexity to the story, suggesting that the ability to form a star relied not only on gravity and chemistry, but also on the subtle, guiding hand of magnetism, a force that could quietly orchestrate the flow of momentum and determine whether a spinning cloud of potential would ever ignite into a star. Yet as we explore the grand cosmic forces of gravity and the intricate dance of gas chemistry, we must also venture into the realm of profound speculation, where the mysteries of the universe's largest structures collide with the puzzles of its smallest particles. This brings us to a hypothesis that connects the birth of the first stars directly to the fundamental nature of dark matter itself. We've already seen how dark matter's gravity sculpted the cosmic landscape, providing the essential scaffolding for gas to accumulate. But what if dark matter did more than just pull? What if it was dynamically active, capable of generating its own energy? This is the fascinating possibility of dark matter annihilation, a process where these elusive particles, upon colliding with one another, could mutually destroy each other, converting their mass directly into energy according to Einstein's famous equation. This released energy would primarily take the form of high-energy photons, electrons, and positrons, which would then inject heat into any surrounding ordinary gas. In the pristine, quiet environments of the first dark matter halos, this exotic heating could have introduced a powerful and unexpected feedback mechanism, subtly influencing the delicate thermal balance upon which star formation critically depended. The impact of this process would have been anything but uniform across the early universe. It would have been intensely concentrated in the very densest regions of dark matter, particularly in the cores of those first minihalos where both dark matter and gas were at their most crowded. This is because the rate of annihilation isn't just dependent on the presence of dark matter, it's proportional to the square of its density. Double the density of dark matter particles, and you quadruple the rate at which they annihilate and release energy. In the deep gravitational wells at the centers of these halos, the dark matter density would have been exceptionally high, potentially making annihilation heating a significant or even dominant thermal factor. This creates a fascinating and counterintuitive scenario. The very places that were most efficient at gathering gas for star formation, the dense cores of dark matter halos, might have also been the places where an invisible energy source was actively working against that process, heating the gas from within and providing a new source of pressure to resist gravitational collapse. The consequences of this are profound. In regions where annihilation heating was strong, it could have significantly delayed the onset of star formation. A gas cloud on the verge of collapse might have been held in a state of suspended animation for millions of years, its internal thermal pressure bolstered by this continuous energy injection from an invisible source. This delay would have allowed the halo more time to accrete additional mass from its surroundings, potentially leading to the formation of an even more massive central object once collapse finally began. In more extreme scenarios, if the dark matter was particularly dense and its annihilation cross-section was high, this heating could have prevented star formation entirely in the smallest halos, effectively setting a minimum mass scale for the first luminous objects. The universe's first lights might then have only been able to ignite in halos massive enough to gather sufficient gas to overcome this internal heating mechanism. This would paint a picture where the properties of dark matter itself acted as a cosmic gatekeeper, determining which regions were permitted to form stars and which were doomed to remain dark. This explanation remains one of the most speculative yet captivating in our list, precisely because it hinges on properties of dark matter that are still entirely unknown and under intense investigation by particle physicists. The critical factor is the annihilation cross-section, a measure of how likely two dark matter particles are to interact and destroy each other upon collision. If this cross-section is very small, then annihilation heating would have been negligible, a faint whisper lost in the roar of gravitational collapse. But if it is toward the larger end of what is theoretically possible, its effects on the early universe could have been dramatic and observable. This transforms the first stars from merely ancient astronomical objects into potential cosmic laboratories. By studying the timing, distribution, and properties of the very earliest stellar populations with telescopes like the James Webb Space Telescope, astronomers might indirectly uncover clues about the nature of dark matter. If we find, for example, that star formation was consistently delayed in certain environments, or that there appears to be a surprising absence of stars in small early halos, it could point toward annihilation heating as the culprit. This beautifully illustrates how the cosmos connects the immensely large to the infinitesimally small, suggesting that the story of how the first stars came to shine may be intimately tied to the solution of one of the greatest mysteries in modern physics, the true identity of the universe's most abundant yet most elusive form of matter. To truly grasp the profound implications of phase transitions, we must first reimagine the infant universe not as a static void, but as a rapidly evolving and seething cauldron of energy, where the very laws of physics as we know them were still settling into their current form. In the first fleeting moments after the Big Bang, the cosmos was unimaginably hot and dense, a unified sea of fundamental forces and particles existing in a state of perfect symmetry. As this frenzied expansion continued, the universe cooled, and at specific critical temperatures, it underwent dramatic and fundamental shifts, cosmic phase transitions not unlike water freezing into ice or boiling into steam, but on a scale and of a nature that is almost impossible to comprehend. These were moments when the underlying rules of reality itself changed, as the single unified force of the very early universe fractured into the four distinct forces we recognize today: gravity, electromagnetism, and the strong and weak nuclear forces. The most significant of these for our story are the electroweak transition and the quantum chromodynamic, or QCD, transition. The electroweak transition occurred when the universe was just a picosecond old, a trillionth of a second after the Big Bang. At energies above this transition, the electromagnetic force and the weak nuclear force were indistinguishable, a single electroweak force. As the universe cooled below a critical temperature of around 10 to the 15th degrees Kelvin, this symmetry was spontaneously broken, granting the W and Z bosons their mass and effectively giving the weak force its extremely short range while leaving the photon massless. This wasn't just a subtle change, it was a radical restructuring of the quantum vacuum that permeates all of space. Now, the QCD transition happened even earlier, at around 10 microseconds old. This was the moment when the primordial quark-gluon plasma, a soup of free quarks and gluons, cooled enough for quarks to become confined together into the protons and neutrons that would later form the nuclei of atoms. The universe underwent a dramatic change of state, from a perfect, free-flowing liquid of fundamental particles to a world where matter was suddenly clumped into discrete, composite objects. The critical idea is that these monumental shifts in the very fabric of spacetime were unlikely to have been perfectly smooth and uniform across the entire cosmos. Just as water freezing on a pond can form ice with cracks and bubbles, or boiling water creates bubbles of vapor of different sizes, these cosmic phase transitions could have proceeded through a process called bubble nucleation. Different regions of space might have undergone the transition at slightly different times, and where these expanding bubbles of the new phase collided, immense energy would have been released. These violent collisions could have created powerful shock waves and, most intriguingly, topological defects in the structure of spacetime itself: one-dimensional cosmic strings, two-dimensional domain walls, or point-like magnetic monopoles. These defects would have been regions of incredibly concentrated energy density, bizarre relics frozen into the expanding universe. This is where the connection to the first stars becomes truly fascinating, though it remains highly theoretical. These defects and the density perturbations left in the wake of the phase transitions would have acted as gravitational seeds of an entirely different nature than the quantum fluctuations from inflation. A cosmic string, for instance, is a flaw in spacetime so dense that a mere inch of it could weigh as much as a mountain range. Its immense gravitational pull would have been phenomenal, acting as an ultra-efficient catalyst for gathering the primordial hydrogen and helium gas. These defects would have provided pre-made, incredibly potent overdensities around which matter could accumulate with far greater efficiency. In regions crisscrossed by the gravitational influence of these relics, the slow, patient work of gravitational instability could have been dramatically accelerated, potentially leading to the formation of the very first structures much earlier than standard models predict. The distribution of the first stars might not just reflect the gentle Gaussian ripples from inflation, but could also bear the imprint of these violent, linear, or point-like scars from the universe's most energetic infancy, a hidden architecture written in gravity and frozen into the cosmos during its first moments of definition. Now, as we've seen how dark matter provided the gravitational scaffolding for the first structures, we can zoom in to witness a more intimate and dynamic process at work within these cosmic cradles. Imagine a vast, invisible sphere of dark matter, a minihalo, its sheer mass warping the fabric of spacetime around it, creating what physicists call a deep gravitational potential well. Think of this not as a physical hole, but as a steep, smooth valley in the landscape of the universe. Now pour a diffuse cloud of primordial hydrogen and helium gas into this valley. What happens? The gas doesn't just sit there. It responds to the irresistible slope of this gravitational terrain, flowing inexorably downhill toward the very center of the halo. This isn't a violent or chaotic rush. It's a serene, relentless funneling, a cosmic focusing effect that gathered the sparse raw materials of the early universe and concentrated them into the specific, dense pockets where star birth could begin. This gravitational focusing was the masterstroke that made timely star formation possible. The early universe was expanding, and without a mechanism to quickly gather gas, this expansion would have continued to dilute matter, making the average distance between atoms greater and greater over time. Gravity alone, acting on the gas itself, might have been too weak and too slow to overcome this cosmic dilution before the window for collapse closed. But dark matter changed the equation entirely. Because it had already clumped together efficiently into halos, it provided these pre-made, deep gravitational wells, these ready-made concentration points. The gas flowing into these wells experienced a dramatic increase in density, and in the physics of star formation, density is everything. Higher density means atoms are closer together, which means they collide more frequently. These collisions are what allow the gas to thermalize, to radiate away energy, and to eventually shed the heat that would otherwise keep it puffed up and resistant to collapse. Gravitational focusing turned a slow, uncertain process into an efficient and inevitable one. The effect was most pronounced in the very first minihalos, those pioneering structures with masses perhaps 1,000,000 times that of our Sun. In these environments, dark matter wasn't just a contributor to the gravity, it was the overwhelming dominant force. The dynamics of everything within the halo were governed by its invisible pull. The gas was merely a tracer, a visible passenger riding the gravitational currents dictated by the dark matter. As the gas sank toward the center, its density didn't just increase slightly. It could rise by factors of thousands or even millions compared to the background density of the universe. This created the extreme conditions necessary to trigger gravitational instability and to make molecular hydrogen cooling effective. The center of a minihalo became a crucible, a natural forge where the universe's simple ingredients were compressed and prepared for ignition. Without this focusing effect, the story of the cosmos might have been drastically different. Gas would have remained spread out, a thin and sleepy haze drifting through the expanding darkness. Occasional pockets might have eventually collapsed under their own gravity, but the process would have been achingly slow, potentially delaying the birth of the first stars for billions of years and altering the entire subsequent history of galaxy formation. The rapid and efficient focusing provided by dark matter halos ensured that the universe woke up from its dark ages on a cosmically rapid timetable. It underscores dark matter's role as more than just a scaffold. It was a cosmic concentrator, a silent architect that didn't just build the rooms but also carefully gathered and placed the furniture inside, setting the stage for the main event to begin. While the universe's first gas clouds were busy collapsing under gravity and cooling through molecular hydrogen, they were also engaged in a constant, invisible negotiation with light itself. This brings us to a subtle yet supremely important property that governed the entire thermal evolution of these nascent stellar nurseries: opacity. In simple terms, opacity is a measure of how easily light, or more broadly, radiation, can pass through a material. A pane of glass has low opacity to visible light. A brick wall has very high opacity. For the first stars, the opacity of the pristine hydrogen and helium gas wasn't just a minor detail. It was a fundamental control knob on the entire process of star formation, determining how efficiently a collapsing cloud could shed its heat and continue its journey toward ignition. In our modern universe, star-forming clouds are filled with tiny dust grains and complex molecules rich in elements like carbon and oxygen. These particles are incredibly effective at absorbing light across a wide range of wavelengths and then re-radiating that energy away. acting as a powerful and versatile cooling system. But the primordial gas had none of this. It was utterly transparent to most wavelengths of light. A photon of visible or infrared light could, for the most part, travel through it for vast distances without being absorbed. This might sound like it would be a good thing for cooling after all. If light can escape easily, so can heat. But the reality is far more nuanced and interesting. This general transparency created a unique challenge. While the gas was clear for most light, it was almost perfectly opaque to one very specific and crucial type of radiation, Lyman alpha photons. To understand why this is so critical, we need to revisit how the primary coolant, molecular hydrogen, actually works. When an H2 molecule is jostled in a collision, it gets excited. It starts to vibrate or rotate. To shed that excess energy and return to its calm state, it emits a photon of a very specific, low-energy wavelength in the infrared part of the spectrum. This is the mechanism that allows the cloud to cool. However, in the dense inner regions of a collapsing cloud, a problem arises. Those freshly emitted infrared photons don't just zip off into space unimpeded. They almost immediately encounter another hydrogen atom. Now, a neutral hydrogen atom has a voracious appetite for photons that carry a very specific amount of energy, the exact energy corresponding to an electron jumping between its first and second energy levels. This is what creates a Lyman alpha photon, and the infrared photon emitted by the excited H2 molecule often has just the right energy to be absorbed by a nearby hydrogen atom. This creates a frustrating game of cosmic hot potato. The energy from the molecular collision is converted into a photon, which is almost instantly absorbed by a hydrogen atom, reheating the gas. That atom then re-emits the photon in a random direction, only for it to be absorbed again a short distance away. The photon becomes trapped, bouncing around endlessly from atom to atom within the dense core of the cloud, unable to escape and carry its energy away into the void. This process is called radiative trapping, and it acts like a blanket, insulating the inner regions of the cloud and preventing them from cooling efficiently. The very center of the collapsing cloud, where densities are highest, becomes a thermal bottleneck. It can get extremely hot, creating a strong outward pressure that resists the inward crush of gravity and ultimately dictates the final stages of the collapse. This delicate dance between transparency and opacity had a direct and dramatic impact on the physical structure of the first protostars. Because the inner core was effectively insulated, it couldn't collapse as efficiently as the outer layers. This led to the development of a much larger, puffier structure for population 3 protostars compared to their modern counterparts. The accretion process, the rate at which gas could fall onto the growing core, was also heavily influenced. The high opacity in the core meant that the intense radiation generated by the infalling material couldn't easily escape, leading to much higher internal temperatures and pressures. This might have actually allowed these protostars to accept a higher rate of accretion without being blown apart by their own radiation, further contributing to their immense final masses. The opacity of the primordial gas, therefore, was not a passive property but an active participant in the formation process, shaping the thermal architecture of the cloud and fine-tuning the conditions that gave rise to the universe's first and most magnificent stellar giants. So far, we've focused on the internal processes within a single gas cloud, how it cools and collapses under its own gravity. But the early universe was not a collection of isolated islands. It was a dynamic and increasingly crowded place. As dark matter halos grew through mergers and gathered into the first protogalactic clusters, the gas clouds within them found themselves living in close quarters. This proximity introduced a powerful new force into the equation, one that could either nurture a stellar birth or snuff it out before it even began: tidal interactions. Think of the ocean on Earth. The moon's gravity doesn't just pull on the entire ocean evenly, it pulls more strongly on the side of the planet facing it. This difference in gravitational pull across an object, the stretching force, is what we call a tidal force. It's the same phenomenon that creates our ocean tides. Now imagine applying that same principle on a cosmic scale. In the early universe, a massive dark matter halo passing near a smaller one wouldn't just gently tug on it. Its gravitational influence would be stronger on the near side of the smaller halo's gas cloud than on the far side. This creates a stretching effect, a tidal force that can dramatically distort the cloud's shape, pulling it out of its serene spherical form and into a long, teardrop-like streamer of gas. The outcome of this gravitational encounter depends entirely on the specific circumstances. In some cases, a tidal force can be the very spark that ignites star formation. As the cloud is compressed and stretched, the increase in density in certain regions can push it over the critical threshold for gravitational collapse. It's like squeezing a stress ball. Applying external pressure forces the material into a denser, more compact state. A gas cloud that was hovering on the edge of stability, too diffused to collapse on its own, could be given that final, decisive nudge by a close encounter with a more massive neighbor. The tidal force acts as a cosmic trigger, jump-starting the process of star birth in an otherwise quiescent region, but the same force can have the exact opposite effect. If the tidal pull is too strong, or if the cloud is not sufficiently bound by its own gravity, the encounter can be utterly devastating. Instead of gently compressing the cloud, the tidal force can simply rip it apart. Gas from the outer layers can be stripped away entirely, siphoned off by the gravitational pull of the passing halo, and lost forever to the intergalactic void. Even if the cloud isn't completely destroyed, a violent tidal interaction can inject a tremendous amount of turbulent energy into it, stirring it up so violently that it becomes too hot and disordered to collapse. In this scenario, a promising stellar nursery is effectively sterilized, its potential scattered by a gravitational encounter. This adds a thrilling layer of drama and randomness to the story of the first stars. It means that the fate of a gas cloud wasn't determined solely by its own mass and temperature. Its future could be decided by the gravitational influence of a distant, passing structure, a cosmic game of billiards where the collisions could either create or destroy. In the clustered environments of the first protogalaxies, these interactions were likely frequent, making tidal forces a crucial and often unpredictable architect of the earliest stellar populations. It underscores that star formation is not a serene, isolated event, but a dynamic process deeply embedded in the gravitational ecosystem of the evolving cosmos. While gravity provided the pull and chemistry offered the coolant, the actual journey of a gas cloud from a diffuse haze to a brilliant star was a story written in the language of heat and energy, a narrative governed by the fundamental laws of thermodynamics. Every collapsing cloud in the early universe was a dynamic thermal engine, and its behavior was dictated by a critical, defining property known as its cooling curve. This isn't a physical shape, but a graph that describes how efficiently a gas can radiate away its heat as its density changes. For the first stars, this curve was starkly simple, dominated entirely by the unique capabilities of molecular hydrogen, and it created a thermodynamic pathway so distinct that it inevitably led to the birth of giants. In the modern universe, the cooling curve for star-forming gas is incredibly complex and efficient. Dust grains and heavy elements like carbon and oxygen can radiate energy across a wide range of temperatures and densities. As a cloud contracts and heats up, these numerous coolants kick in at different stages, acting like a sophisticated, multi-stage climate control system that keeps the gas temperature relatively low and allows the cloud to fragment into many small, dense cores. This is why we see stars born in large families with a wide range of masses. The primordial universe had no such luxury. Its cooling curve was minimalist, relying on a single, fragile mechanism. Molecular hydrogen is an effective coolant, but only within a specific thermal window. Its efficiency peaks at around 100 degrees Kelvin and again at several thousand degrees, but it becomes much less effective at very high temperatures. This created a very particular thermodynamic journey for a collapsing population 3 cloud. As a vast cloud of pristine gas began to feel the grip of its own gravity, it started to compress. This compression, as we know, causes heating the same way a bicycle pump gets warm with use. Initially, the molecular hydrogen within the cloud was efficient at radiating this heat away, allowing the cloud to continue contracting. But as the collapse accelerated and the core density and temperature soared, the gas approached a thermodynamic crossroads. The cooling from H2 began to level off. It couldn't keep pace with the prodigious amount of heat being generated by the violent infall of material. The cloud's temperature, instead of staying low, began to rise sharply. This created a powerful thermal pressure that started to fiercely resist further gravitational collapse. It was a classic standoff between the inward crush of gravity and the outward push of heat. This specific juncture in the cooling curve is what set the destiny for the first stars. The point at which heating finally overcame cooling set a minimum mass scale for collapse. It defined the gene's mass. Because the primordial gas couldn't cool to the very low temperatures of modern clouds, this minimum mass was enormous. Only the most massive clouds or the most massive fragments within a cloud possessed enough gravitational muscle to overcome this intense thermal pressure and continue collapsing. The thermodynamics of the system acted as a filter, weeding out smaller potential stars before they could even get started. A cloud that began with enough mass would eventually see its core temperature rise to the point where molecular hydrogen cooling became efficient again, allowing the final, furious stages of collapse to proceed. But the die was already cast. The star that formed would be massive by its very nature, a consequence of the fundamental thermal properties of a pure hydrogen-helium gas. This explanation beautifully roots the entire spectacular process in the most basic physical principles of energy and motion, showing how the universe's first light was ignited not by magic, but by the relentless and predictable laws of thermodynamics. But to truly appreciate the grand stage upon which these first stars were born, we must pull our perspective way back, from the intimate collapse of a single gas cloud to view the cosmos on its largest possible scale. The universe, as we now understand it, isn't a random scattering of galaxies floating in empty space. Instead, it is structured into a vast, intricate, and beautiful architecture known as the cosmic web. This magnificent framework consists of enormous, thread-like filaments of dark matter that stretch across billions of light-years, connecting at dense nodes or junctions where massive galaxy clusters reside. Between these filaments are vast, empty voids, regions of startling emptiness that make up most of the volume of the universe. This web is the largest pattern in nature, and it was within this overarching structure that the story of the first stars unfolded. For the primordial gas that would become those first stars, these dark matter filaments were far more than just scenic background features. They were the essential superhighways that delivered the raw materials for creation. After recombination, the neutral hydrogen and helium gas was not sitting still. It was in motion, responding to the gravitational landscape sculpted by the invisible dark matter. The deepest gravitational potentials were found along the lengths of these filaments, and even more so, at the nodes where they intersected. Gas began to flow along these invisible roads, streaming from the emptier void regions inward toward the denser filaments, and then flowing along those filaments toward the waiting gravitational wells of the first dark matter halos. This wasn't a sudden, catastrophic collapse, but a continuous, large-scale funneling of matter, a slow and steady river of potential flowing into the reservoirs where star formation could begin. This process solved a critical problem for the first stars, the supply chain. A protogalactic halo sitting at a filament node didn't have to rely solely on the finite amount of gas it initially captured. It was constantly being fed. Fresh, cold, pristine gas was delivered along these cosmic arteries, providing a sustained inflow of fuel that could continue to feed the growing protostar at the halo's center. This constant replenishment helped overcome another potential barrier, feedback. As the first stars began to shine, their fierce radiation threatened to heat up and disperse the surrounding gas in their immediate vicinity, potentially shutting off their own fuel supply and limiting their growth. But with a continuous stream of new, cold gas flowing in from the wider filament, this feedback could be mitigated. The incoming material could replenish what was being lost, allowing star formation to continue and potentially enabling the formation of even more massive objects than if the halo had been an isolated, closed system. The geometry of this web didn't just influence how stars formed, it dictated where and when they would form. The first points of light in the universe didn't just appear anywhere. They ignited at the nodes of the cosmic web, at the intersections of these great dark matter highways. The very first stars likely formed in the smallest, earliest nodes. Then, as the web evolved and grew over millions of years, larger halos built up at the intersections of more and more filaments, creating the sites for the most intense and prolific star formation. The location of a halo within the web determined its entire history. A halo sitting at a major intersection of several thick filaments would be showered with gas, growing rapidly and forming stars early and often. A halo on a minor, isolated filament might receive only a trickle of material, delaying its star formation or preventing it altogether. The cosmic web was the universe's ultimate architectural blueprint, and the pattern of the first starlight was nothing less than a direct tracing of this hidden, dark matter skeleton, a glowing map of the largest structure in existence. Yet after exploring the profound influence of the cosmic web's grand architecture, we must now venture to the opposite extreme, to the very smallest scales imaginable, where the familiar rules of physics break down and the fabric of reality itself becomes a seething, chaotic foam. This brings us to the final and most speculative of our 35 explanations, a concept that stretches the boundaries of known science to its absolute limit: the potential role of quantum gravity in the birth of the first stars. To even approach this idea, we must grapple with the greatest unsolved problem in theoretical physics: the stubborn refusal of Einstein's theory of general relativity, which governs the very large, to peacefully coexist with quantum mechanics, which governs the very small. At the energies and scales present in the first moments of the universe, these two pillars of modern physics would have both been in play, and their violent disagreement suggests that our current understanding of that era is, at best, incomplete. It is within this gap in our knowledge, this chasm of ignorance, that fascinating possibilities reside. One of the most compelling speculations involves the concept of space-time foam. The idea, first proposed by the legendary physicist John Wheeler, suggests that if we could peer down to the Planck scale, a distance of 10 to the negative 35 meters, the smooth, continuous space-time we experience would dissolve into a chaotic, probabilistic froth. At this unimaginably tiny scale, the very notions of space and time would lose their meaning. Quantum fluctuations would be so violent that they would create a bubbling sea of virtual black holes and wormholes, constantly popping in and out of existence. The geometry of spacetime would be in a state of constant, turbulent fluctuation. This isn't just empty theorizing. It is a direct consequence of applying the uncertainty principle to the gravitational field itself. The energy required to probe such tiny scales is so immense that it would warp spacetime into a frenzy of topological change. Now, consider the implications of this for the very first structures. The initial density fluctuations that seeded all cosmic structure were born during inflation, which occurred when the universe was in an energy regime where quantum gravity must have been dominant. It is not a stretch to imagine that the properties of this spacetime foam could have imprinted itself onto those fluctuations. The quantum jitter of spacetime itself could have provided an additional, subtle source of primordial noise, slightly altering the spectrum of density variations that inflation stretched across the cosmos. This means the gravitational blueprints for the first stars might carry not just the signature of quantum field fluctuations, but the faint, frozen echo of quantum spacetime itself. The distribution of the first dark matter minihalos, and therefore the first stars, could be influenced by the underlying foam-like structure of reality, making the large-scale architecture of the universe a direct reflection of its smallest-scale nature. Furthermore, this speculative physics could have played a more direct role during the collapse of the first gas clouds. The immense densities reached in the cores of these collapsing protostars would have created gravitational fields of unbelievable strength. In such an environment, the effects of quantum gravity might have become non-negligible, potentially modifying the very laws of physics at the critical moment of stellar birth. Some theories suggest that quantum gravitational effects could provide a new source of pressure, a repulsive force that would counterbalance gravity at extremely small scales, preventing a total collapse into a singularity, and perhaps stabilizing the formation of the first stellar cores in a way that classical physics cannot describe. Alternatively, the existence of microscopic wormholes or tunnels in the spacetime foam could have provided a novel mechanism for energy or information transfer, acting as a conduit that allowed heat to escape the dense core more efficiently, thereby facilitating the final stages of collapse in a manner we cannot yet model with our current theories. This explanation, while standing firmly on the frontier of knowledge and dipping into the realm of informed speculation, serves a profound purpose. It is a testament to human curiosity, a declaration that our quest to understand the first stars does not end with the known laws of physics, but pushes us to confront the deepest mysteries of existence. It connects the spectacular, brilliant birth of a star to the silent, invisible turmoil of the quantum vacuum, suggesting that the universe's first light may have been kindled not just by gravity and chemistry, but by the very nature of spacetime and reality at its most fundamental level. It is a humbling reminder that for all we have learned, the cosmos still holds secrets that lie beyond our current grasp, waiting for a future theory of everything to reveal the final, breathtaking chapter in the story of how something as magnificent as a star could emerge from nothing but a quantum whisper in the void. And so, as we stand back from this breathtaking cosmic tapestry, we see that no single thread alone tells the whole story. Each of these 35 explanations is a vital piece of a magnificent puzzle, interlocking to reveal a process of breathtaking complexity and profound beauty. The birth of the first stars was not a simple event but a grand symphony composed by the universe itself, where gravity provided the dominant rhythm, chemistry added the delicate melody, and fundamental physics set the overarching harmony. From the faintest whisper of quantum uncertainty stretched across the cosmos to the silent, gravitational embrace of dark matter scaffolding, every force and condition played its part in this cosmic dawn. It was a concert of conditions unique to that pristine era, a moment in time that will never be repeated, where simplicity gave way to complexity and darkness was forever banished by light. This grand synthesis shows us the true power of multidisciplinary science. We cannot hope to understand the first stars through astronomy alone, or through particle physics or chemistry in isolation. It is only by weaving these insights together that the full picture emerges. The quantum physicist studying inflation, the cosmologist mapping dark matter, the astrochemist modeling molecular hydrogen formation, they are all telling different parts of the same incredible story. It is a story that connects the very largest scales of the cosmic web to the very smallest scales of the atomic nucleus, proving that the universe is a deeply interconnected whole. The ignition of that first star was the culmination of a chain of events that began with the fundamental laws of nature themselves, a testament to the fact that from a handful of simple rules, infinite complexity can arise. What emerges from this synthesis is a profound new appreciation for the universe's capacity for self-assembly. The cosmos was not built by an external hand. It built itself, using the tools of physics and chemistry to transform a formless fireball into a structured, luminous universe. The first stars were both the product and the architects of this transformation. Their birth created the conditions for everything that followed, for galaxies to assemble, for planets to form, and for life to eventually emerge. In their brilliant, short lives, they forged the first heavy elements, seeding the cosmos with the raw materials for future generations of stars, for rocky worlds, and ultimately for us. To understand them is to understand our own deepest origins, to trace our lineage back to those first, magnificent giants that lit the fuse of cosmic evolution. This journey through 35 explanations is more than just a catalogue of physical processes. It is a reminder of humanity's insatiable curiosity and our relentless drive to comprehend our place in the cosmos. It showcases our ability to use reason, observation, and imagination to peer back across 13.8 billion years and reconstruct the universe's first moments of light. The story of the first stars is one of the greatest detective stories ever told, and we are the detectives, piecing together clues from the cosmic microwave background, from sophisticated computer simulations, and from the laws of physics themselves. It is a story that is still being written, with new chapters added every time a telescope like the James Webb Space Telescope peers back to the edge of time. And as we continue to unravel these cosmic mysteries, we do more than just satisfy our curiosity. We fulfill a fundamental human need to connect with the cosmos and understand the magnificent chain of events that led from an empty darkness to a universe brimming with light, life, and wonder. The birth of the first stars was not a single event but a magnificent symphony of physical processes, a cosmic orchestra where each instrument, from the deep bass of gravity to the high strings of quantum mechanics, had to play its part in perfect harmony to turn a featureless universe into a canvas of light and structure. We've journeyed through 35 astounding explanations, and each one reveals a new layer of this profound narrative. From the relentless gravitational collapse that gathered the primordial gas to the delicate molecular hydrogen cooling that allowed it to condense, every mechanism highlights the sheer ingenuity of nature in overcoming immense obstacles to create something truly magnificent. It was a chain of events so precisely tuned that altering any single link might have left the universe in perpetual darkness. This story isn't just about ancient suns, It's about the fundamental processes that set the stage for everything we know, including us. As we continue to study these ancient luminaries with powerful tools like the James Webb Space Telescope, we are doing more than just peering into the distant past. We are deepening our understanding of our own origins. Every element in our bodies, every planet orbiting a star, every galaxy spinning in the void, all of it was made possible by that first generation of stellar giants. They were the universe's first alchemists, transforming simple hydrogen and helium into the carbon, oxygen, and iron that would eventually form planets and life. Their story is our origin story, a critical chapter in the universe's grand narrative that connects the first moments after the Big Bang directly to the world we inhabit today. This ongoing quest for knowledge reminds us that we are not just observers of the cosmos but active participants in its unfolding story, continually seeking to understand our place within it. We've covered so much ground, from dark matter's invisible scaffolding to the potential influence of quantum gravity, but the conversation doesn't end here. I'm incredibly curious to hear which aspect of this journey resonated most with you. Was it the sheer power of gravitational collapse, the fragile beauty of molecular hydrogen chemistry, or the mind-bending idea that quantum fluctuations seeded the entire cosmic landscape? Share your thoughts in the comments below. Let's keep this discussion going. If you enjoyed this deep dive into the cosmic dawn, please show your support by liking this video and subscribing to the channel for more explorations into the universe's greatest mysteries. Thank you for joining me on this incredible journey to the edge of time and the dawn of light. Until our next adventure.